All right, cool. So this is spring 2024, 1410 review session. So I'm going over all of Calc Blue volumes 1, 2, 3, and 4, some main topics. And also I have examples scattered throughout the exam or the review today. Okay, so volume 1, here is what we'll go over. So the dot product, cross product, lines and planes in space. So like all those like finding equations of planes and stuff, all about curves, matrices, and row reduction. So this was all volume 1 stuff. So just as a reminder of how dot product works, you multiply terms component-wise and add them up together. So like dot product of 1, 2, 3 with 4, 5, 6 would be 4 plus 10 plus 18. And remember that the length is each component squared, add them up, and square root them. There are some properties of dot products like commutativity, so it doesn't matter which order you write them in. There's also this angle formula, don't forget that. So if you wanted to find an angle between two vectors, u and v, this is the formula that relates their angle together. Okay. And so I have an example there. And remember, this is a very important fact that if you dot product two vectors and you get 0, that means that those vectors are orthogonal. Okay, then we have cross product. So cross product, remember that you don't really need to memorize the formula. A nice trick for remembering how to do cross product is you write ijk as the first row, your u vector as the second row, and your other vector as the last row. And remember that this is equivalent to if you wrote these things as each column. So if you wrote them as columns, you'll get the same answer. And that's using the rule that the determinant of a matrix is equal to the determinant of its transpose. Okay, and let's see. Remember that a cross product, the result of it is always perpendicular to both u and v. So this comes in very handy for a lot of the plane problems, like finding normal vectors of planes and everything, which I have some examples later on. Okay. Also remember that there's this area formula, so you can use a cross product to, yes, I have a question in the chat to, yeah, mute the doorbell sound. Yes, I'm sorry. Let me see. Pause. Okay, so resuming the recording. So we have the area of a parallelogram can use this cross product formula. And we also have the scalar triple product. So remember a nice, did you guys hear that sound?
Yeah. No, it's okay.
Okay. Sorry, I don't know why I turned it off. All right, anyway, scalar triple product. Another way of finding the scalar triple product is that you could do a determinant. So you write each of the vectors as columns, or you can write them as rows. All of my notes are on my website, which is tinyurl.com/irishorn. And it's also maybe someone, I put it in the chat as well. Okay, let's see. And remember things about the cross product, right? Like the right-hand rule. So if you had a vector like u that goes like this, and a vector v that goes like this, and you want to find u cross v, well, you start, like you use your pointer finger and you point it towards u. And then you want to curl your fingers towards v. So wherever my thumb is, that's where the cross product is. So in this case, my thumb would be pointing out of the page. So this cross product points out of the page. Right, and so review that quiz question where there's a lot of these different versions. All right, let's look at some lines and planes then. All right, so how do we write a parametric equation of a line? So in general, we want a line through some point and pointing in some direction, right? So this direction is kind of like our vector that we're going to use, and we're going to take that vector times some variable. I can call it t, plus my starting point. So let's say, for example, I wanted to find the line through this point and parallel to this vector. Well, then my answer is that I could write r, my line, as the point, the initial point, plus t times the vector, which is -2, 0, 4. I could also have written it in like a more parametric way where I write each component. So x would be like the first term minus 2t. So -2 minus 2t. Y would be 0 plus 0t, and z would be 4 plus 4t. Okay, and then whenever we write a line, remember that we usually want to write it parametrically, meaning like there's like different components like x, y, z's with this t. Whenever we write a plane, we always want to write it implicitly, meaning like it's like one line, like something equals 0, or something equals some number. So how do you write a plane? We need two things. We need the normal vector, which you can think of as a slope. It's not really a slope, but you can think of it like that. And we need a point. And we usually do that normal vector, which would be n, so nx, ny, nz, dot with some original like coordinate letters that we're using, like x, y, z, minus the original point that lives in our plane, x naught, y naught, z naught. And you set that equal to 0. And now the way you simplify this is you have your normal vectors. Inside here, this would be x minus x naught, y minus y naught, z minus z naught. So you did it component-wise. And then you finally take the dot product. So the x component of the normal vector times x minus x naught, plus this y minus y naught, plus this z minus z naught equals 0. Shouldn't the slope be the 2, 4, -2? 2, 4, -2. Yes, I wrote it. Yes, I wrote the numbers wrong. Thank you. This is 2, 4, -2. Okay. Okay, so that was the plane. Questions so far? Okay, so as I said, remember if you're writing a line, think parameterization. If you're writing a plane, think implicit. All right, now the nice property about these planes that usually comes up is like, say you have two vectors that are tangent. Tangent meaning they are on your plane, like literally. But say you wanted to find the equation of the plane. Well, to find an equation of a plane, you need that normal vector. So I could take those two tangent vectors, which are v1 and v2, and take the cross product. Because I know that the cross product will give me the normal vector. Equals normal vector. And that's because the cross product is orthogonal to like each of the things. So n is orthogonal to v1 and also orthogonal to v2. All right. And I'll just note that also sometimes this scalar triple product is usually used to, well, what is the scalar triple product, right? We're doing the determinant of u, v, and w as each of the columns. And that's like kind of like finding the oriented volume of the shape that is spanned by the u vector, the v vector, and the w vector. Like I might get this like cube thing. And so if we found this volume of parallelepiped and end up getting 0, well, what does that mean? If we get something that has a volume of 0, that means that it has no like, it's flat, it's in 2D. And so another way of saying something is coplanar is saying that the scalar triple product is 0, because that means everything is flat on the same plane. There's no volume at all. Okay. So here I have a question. An example from the Calc Blue book, week 1, question 1. So here we have, consider the following planes in R3 where C is constant. So we have these two plane equations. Part A says, assuming C equals 1 and Z equals 0, find the point of intersection along these two planes. Okay, so we have two planes and we have this C equals 1, Z equals 0. Let's first plug those into our equations. So when I plug in C equals 1, I get 2x minus 3y. Well, 1 plus 4 is 5. So I have 5z, but z is 0. So this becomes 0. So I just have 2x minus 3y equals 5. And I do the same thing with the second equation. Well, how do you find the intersection of two things? Like, no matter what it is, if it's a plane or if it's two lines, whatever, usually you set them equal to each other. So that's exactly what we can do. And specifically, setting them equal to each other, well, we could use different techniques like substitution, elimination, whatever we want. Because there's this 2x and a 2x, I'll just use elimination. So I get -4y equals 4 or y equals -1. So now I know z equals 0, y equals -1. Now I just have to solve for x. So I can use any one of my equations. Let's just use this first equation and say 2x minus 3y is now -1 equals 5. So 2x plus 3 equals 5, or 5. 2x equals 2, x equals 1. So the point of intersection is 1, -1, 0. Okay. Part B says, assuming c equals 0, find a vector that points along the line of intersection between these two planes. So here I'm going to use this, we can use this picture here. Oops. So we have these two planes, right? For example, this blue one and this orange one, or this red one. And I want to find the line of intersection. I want to find this green line. Well, how could I find that? Notice that the blue plane has its normal vector, right? I could call it B. The red plane also has its normal vector, which I could call R. And remember that the cross product result is always orthogonal to both things. So if I took the cross product of R cross blue cross B, then I'll get this green vector, which is exactly what I want. That's the line of intersection. So if C equals 0, how do I find that vector of intersection? First, I'm going to plug C into my equations so that I have my plane equations. So when I plug in 0, I get -3y plus 4z equals 5. That's my first equation. And plug C equals 0 into this equation, I get x minus z equals 1. So these are my two planes. What is the normal vector of this one? Well, you look at the coefficients. There's nothing in front of x, so 0. Y has a -3, z has 4. The normal vector of this plane is 1, 0, -1. And I take the cross product. So what is the cross product of these two vectors? I'm going to do it the determinant way. So I get I times 3 minus 0 minus j 0 minus 4 plus k 0 minus -3. So this is 3i plus 4j plus 3k. So the line of intersection points in the direction of 3, 4, 3. Questions on this problem? Okay, and in my notes, I have a second method of solving this if you want to look at it using parametrization. So kind of like the elimination method. Both work. All right. Then we have like the arc length formula. So length is the integral of the arc length. Let me not do these. Okay, let me move on to matrix multiplication. All right. So remember that in general, matrix multiplication is not commutative. It's only commutative in a few special cases. And that's where, say, both matrices are diagonal matrices. So there's only numbers on the diagonal. Then matrix multiplication is commutative. It's also commutative if one of the matrices is a scalar multiple of the identity. So like here, A could be anything it wants to be. As long as B has like the same numbers on the diagonal, that means it's a multiple of the identity, then A times B will equal B times A. So matrix multiplication is commutative. We also have, how do you do a transpose? Each of the rows becomes the columns. All right, determinants. For 2 by 2 matrix, the determinant, you always follow this formula, which is AD minus BC. If you have a higher dimensional matrix and you want to take its determinant, you can use different methods. There's this crossway, which works. There's also the second method of minor expansion. So you choose one column or one row to expand. For example, here I chose it looks like I chose the first row. I did A11 times, I cross out the remaining stuff and I'm left with this 2 by 2 matrix, which is here. Then minus, remember the signs alternate. Minus A12, And then I imagine crossing out that row and column, and I'm left with this 2 by 2 matrix here, and so on. And later on, we learned the row reduction way, which I'll also go over later. Okay, let's see. Some common tricks of determinants. If you have an upper triangular matrix or lower triangular matrix or diagonal matrix, the determinant is just multiplying the diagonal terms. Also, this property, sometimes people get confused. Or actually, yeah, this property. So say they gave you A is some 2 by 3 matrix and B is some 3 by 2 matrix. Well, then if we wanted to find the determinant of AB, people say, oh yeah, it's equal to the determinant of A, determinant of B. And since A is not square, they say this is not possible to find and it doesn't exist. But you can't just automatically do that. You can only use this rule if A and B are both square matrices. Okay, and like the matrix multiplication is, of course, has to be possible. So even though A itself and B itself are not square, the determinant of AB, you can still find it because you can still multiply A, B together first. You multiply the 2 by 3 matrix by the 3 by 2 matrix, and you get a 2 by 2 matrix, which this is square. So we can find its determinant. Determinant possible. Okay, and let's see. Also know that if you take the determinant of 2 vectors itself, that gives you like the area of a parallelogram. And this was the triple scalar product, where you take the determinant of 3 vectors. That gives you the volume of a parallelepiped. We also have some nice properties with block matrices. So block matrices, you can like multiply them together. You could take the inverses, the determinant. You can also get similarly multiply like the diagonal terms. So for example, if I had a block matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. Then this is equal to, and I wanted to find its inverse, for example. Then A inverse will be, well, whatever is the inverse of this 2 by 2 matrix, I would put those numbers there. And then what is the inverse of 5? Well, that's like taking the reciprocal, so it's 1/5. And then whatever the inverse of this 2 by 2 matrix is, that would go there. And then the rest are all like zeros. You can fill in all the zeros. Okay. Questions so far? Okay. Feel free to, yes, question?
Do you mind repeating that last part again?
Yes. So if I had a block matrix like this for A, and I wanted to find A inverse, instead of like taking this whole 5 by 5 matrix and trying to do like a bunch of row reductions or whatever to find the inverse, I could look at each block separately. So I look at this 1, 2, 3, 4, and I see what is its inverse. Well, the inverse of 1, 2, 3, 4 would be 1 over the determinant, which is 4 minus 6. I swap the main diagonal, so this is 4, 1, and I negate the off diagonal. So I take the negative of the off diagonal. So I get, this is -2, 3 over 2, 1, and 1/2 negative. And so I would write those 4 values at the top left corner. So I could just take the inverse of this itself and write it here. Then this 5, what is like the inverse? It's basically the reciprocal. So I do 1/5. And then for this 2 by 2 matrix, I do the same thing and I find that inverse and I can write those 4 numbers here. Other questions?
Wait, so for that like methodology for finding the inverse, how do you know when you can use it and when you can't? Like, does it have to be that specific like method where it's like 2 blocks and like 1 number in the center?
No, it could be any like size blocks you want, but they have to like all be on the diagonal. So it has to be a block matrix to use this formula. Block matrix meaning I could have like a 2x2 block here. I could have a 3x3 block here. I could have a 1 block. It doesn't matter as long as they are all on the diagonal. This could be like a number, like that. And everything else has to be zeros. So like all the other numbers have to be zeros. Then you can use this method. So it could also be like, I don't know, you could have one number here. You could have a 2x2 block here. You could have a 5x5 block here. Whatever sizes you want. Okay. Does that make sense? Questions on this block matrix? So the reason why it's called block matrices is like because there's like little blocks, square blocks, all on the diagonal, and everything else has to be zero. I have a question in the chat. Can you repeat why we do the cross product to find vector pointing along intersection? Oh wait, so none of the entries for the blocks can be zero. Oh, the entries in these blocks could be zero if you wanted them to. Like you could have a 0 here, that's fine, but you have to like be able to distinguish that it's like a block. So like if all these numbers were 0, that would probably not really make sense. Like you probably don't want to do a block matrix method with that. But you could have like, if you had like a number here, 5, 4, like that's fine. That still looks like a block. Okay. And why does the 5 become a 1/5 and not negative 1/5? So it becomes a 1/5 and not a negative because recall that A times its inverse has to equal the identity matrix, right? So if we multiplied A times A inverse, what do you do to get the middle like term? You do this row times this column to get the middle term, and you need it to be 1 for it to be an identity matrix. If this were negative 1/5, you'd get your identity matrix, you'd get like some number, you get -1 here, which you don't want. Okay, and the thing about the cross product for the intersection is because of this picture here, where if you have two vectors like R and B, when you take the cross product, that result is going to be orthogonal to the blue one and orthogonal to the red one. So here's orthogonal, here is orthogonal. And that, because they're both orthogonal, that will give you this green one. Like, yeah. And here, I guess this picture, it looks like the planes are orthogonal already, but it really works for any, like, no matter what the planes are. Like in this example, it just doesn't, it's a little bit harder to see with this right example, but you see how like this normal vector of the orange plane and this normal vector of the purple plane, if you cross product it, you'd get this green vector that points like this or this. And that's along the intersection of those two planes. Okay, so whatever the result of your cross product is orthogonal to both of the vectors that you used. Just like why when we're on a plane and you have two tangent vectors, U and V here, like why does the cross product give you the normal vector? That's the same reasoning. Why would you do that when you can just return the intersection vector, which is also parallel since it's the same? You could. In this question though, for part B, they like changed the constraints, like they made C equal 0 instead, whereas in part A, C was 1. And so your question about just return the intersection vector, in my notes, I have a second method for how to solve part B, and that's how you do it. You use the intersection vector. Okay. All right, let's move on to row reduction. Okay, row reduction. The main key thing to always remember about row reduction is like, why are we using it? It's because basically a bunch of problems that we're going to do are all boiled down to AX equals B. So how do you solve a problem like AX equals to B? Oh, I have a question related to, can you go over how you know if a vector is parallel or perpendicular? So a vector is, so if the dot product of two vectors is 0, that means that U is orthogonal to V or perpendicular. To see if they are parallel, well, if you want U to be parallel to V, we see that the angle between the two vectors is 0, right? There's no angle. They're like literally on top of each other. So you could try using the cosine theta equals UV over the length formula. Right. And so we want, let me see, if we want the angles to be 0, cosine of 0 is 1. So if two vectors dot producted over their lengths gives you 1, then that means that they're parallel. Okay, and this formula actually is also useful for other problems where it's like, which of these vectors are acute or which of these vectors are obtuse, things like that. You want to use this formula. And so like if U dot V, if you multiply, I think this was also a quiz question. So look back at like week 1 or something. If these numbers give you, if the dot product gives you a positive number, well, that means that cosine of theta is a positive number, right? And when is cosine theta positive? Over here in this region. Cosine theta is always positive from 0 to pi over 2. So if the dot product is greater than 0, you know that you have an acute, that vectors form an acute angle. If the dot product is less than 0, that means that cosine of the angle is negative. When is cosine negative? Over here. That means that your angle is probably obtuse. Okay. All right, so back to the how do you solve AX equals to B. So one method is you do an augmented matrix and you row reduce. So I write the matrix A and then I write B as like at the very right-hand side, do a bunch of back substitution and try to solve. So I'll have some examples. But let me also mention the second method, which is that, well, I can multiply the inverse of both sides by A inverse. Sorry, let me rephrase that. I can multiply both sides by A inverse. So when I do that, I get X equals A inverse B. Note that you only want to do this if A is square and invertible. If A is not square or like not invertible, don't automatically assume that there's no solution. There still possibly could be solutions. Like it might be infinitely many solutions. So if it's not square or not invertible, always do this first method. But if your matrix is square and invertible, this is the fastest method. All right, so let's see. Three main row reductions to note are, one, you can exchange two rows. When that happens, it multiplies the determinant by -1. You can also rescale. Whatever you multiply by, that's what it multiplies the determinant by. And there's also combining. So you could take one row and add or subtract a multiple of another row to it. And notice that the reason I always write like some row equals the row itself plus something else is because this is what's considered a combination. If you try to do something like row 1 is 2 row 1 plus 2 row 2, you're really doing two elementary operations at the same time. This is you're rescaling by 2, and then you're doing a combination. So you can't just say this is a combination. This is only important because when we find a determinant, we have to keep track of what is changing. So if you do this together, you're technically rescaling by 2 and a combination. So that's why I always recommend writing it separately. Like row 1 equals what is happening to row 1. Maybe I want to multiply it by 2. And then I'll take that new row 1 and add 2 row 2 to it. So like I write each elementary operation separately. Okay. So, and people are always confused about this rescaling thing. Let me do a small example. If I have this identity matrix, right? And I rescaled row 1 time, let me just do 2 times row 1. Then the first row becomes 2, 0, 0, 1, right? And so usually we have the case where this matrix A is too hard to find, but instead we can find the row reduced matrix. So what is the determinant of the row reduced matrix? It's 2, because I multiplied the diagonal. But the question wasn't to find a determinant of R. The question was to find a determinant of A. So how do I go back to the determinant of A? I do determinant of R divided by anything that happened. What happened? I rescaled by 2. So I put the 2 down here. So I get 2 over 2, which is 1, which I was correct. The determinant of identity matrix is 1. So I always divide by whatever happened. Was that for finding the determinant via row reduction? Yes. If you want to find the determinant via row reduction, this is what you do. Do a bunch of row operations, get the nicer matrix, which is usually easier to get the determinant of, and divide by whatever row operations you did. Okay. Okay, how do we find inverses? So for 2 by 2 matrices, there's the formula for how to find inverses. For higher dimensional matrices, you have to do row reduction. So you always write your matrix A, which says like 1, 2, 1, 2, 3, 4, 5, 6, whatever you want. 0, 1. And then you write an identity matrix of the same size, like this. And you want to row reduce until you get that identity matrix back on the left-hand slide. And whatever is here will be your inverse. Okay, it's important that you get the actual identity matrix on the left side. All right, another thing that came up on the quiz was this formula here, where the dimension of your space minus the number of equations equals the dimension of your solution. So this is like something to memorize. So as an example, say we're given this augmented matrix here. You always want to row reduce, which they've already given to us, or kind of given to us. How else could we row reduce this? Notice that like I want numbers on the diagonal. So let me switch row 2 with row 4. When that happens, I have this first row. The fourth row now becomes the second row. The third row is the same. And the second row goes to the end. Okay. Oh, I'm also going to switch the second row so I'm going to make it. I want it to be like this. Okay, so I did 2 things. Whatever I did. All right. The reason I did that is because now I see that we have these pivots, these leading numbers for each of the rows. And so that means that my number of equations I have is actually 4. Number of equations equals 4. If I have row reduced and I got like a 0 here, that means that I only have 3 rows with leading numbers, and so the number of equations would have been 3. But right now I have equations equal to 4. Okay, so we have that part. What is the dimension of the space? Well, notice that like we are given this augmented matrix. What does the augmented matrix really mean? What it really means is that we're doing this matrix times whatever our input is. So we have x1, x2, x3, x4, x5, x6 equals this vector. This is like an AX equals B question. So that means that the dimension of my space is, well, my input space is this. I have 6 terms here. So the dimension of space is 6. Because I have 6 variables. I'm using 6 variables. And so using this formula here, the dimension of my space minus number of equations, 6 minus 4 equals 2. So this quiz question was like, the solutions of the corresponding system of linear equations form a 2-dimensional shape in R6. Okay, so the solution set is 2D living in R6. Okay, questions so far? All right, then we have linear transformation. Oh, yeah, question?
Yeah, I have a question. So if you go a bit back up,
Mhm.
so in the lower matrix, you highlighted the numbers.
Yes.
The way you determine the equations is only if you have a leading number.
Yes.
So then if instead of that one, we would have 0, then
Mm-hmm.
that would mean just 3 equations. Or
Um,
that would still mean 4 equations because you still have the other 5 variables in that equation, no?
it would depend on if things like row reduce. So like see how this 2 here, I could get rid of the 2 by subtracting 1/2 of row 2 from it. So like I would have to keep row reducing everything, and probably this would become a 0. And then I could probably use this row to get rid of this 3, and it would become a 0. And then I could use this row to get rid of the 4 and become a 0.
So you
So
want to reduce until you have a triangular matrix? Or
yes. Yep.
and does it matter if it's upper or lower triangular, or that doesn't?
You should do upper triangular.
Okay.
Yep. So in this case, if that had happened, I can use like each of these rows to like get rid of those numbers. And then so if I row reduce, this row would probably come to the bottom. And actually I would still have 4 equations though, because now it just like shifted a little bit. Okay. But if like say this was also, if this was all zeros, then we only have 3 equations. Okay, could you please repeat what we use the pivots for? Yeah, the pivots are just to see how many equations you have. So you want to row reduce as much as possible to an upper triangular matrix and see like how many leading numbers you have. And that's the number of equations. The reason is because like if you get a row of zeros, for example, that just means that one of the equations was redundant. Like it gives you the same like repeated information. And so you don't really want that. You don't want the redundant one. So we only want to look at what is important. And it's a 6-dimensional space because there are 6 columns. Yes, you can look at it that way. 6 columns. Yeah. Does the size of the matrix matter for row reduction? The size does not matter for row reduction. You can always row reduce no matter what size the matrix is. Okay. Other questions? For augmented matrix, we always assume the last column is not exactly, yes. The last column of the augmented matrix doesn't count as a variable. That was something that people missed on the quiz. For a redundant equation does that mean the last column after dashes is 0, or it could be any number? The last row, this number, it could still be a number. We count equations, we only care about everything to the left of the dashed line. So it doesn't matter like what's over here. If we have a row that is a scalar multiple of another row, then we don't consider it. Yes, because if you have a row that is a scalar multiple of the other row, like for example, like this, say we had an augmented matrix like this. What happens when we row reduce? If I do row 2 is row 2 minus row 1, that becomes 1, 2, 3, 4, 0, 0, 0, negative 1. And so how many leading numbers do I have? I only have 1 leading number. So that's 1 equation. Okay, but there's 3 columns still, so 3 variables. My dimension of space is still 3. Okay, let me go into linear transformations. Okay, linear transformations, right? Any matrix represents any linear transformation can be represented as a matrix. So the simplest linear linear transformation is the identity matrix, where the linear transformation that it does is nothing. Everything stays the same. Okay, common types of linear transformations. We have rescaling. That's where you rescale an axis independently. So recall, how do you write like a matrix? let's say we see this transformation. I look at what happens to the 1, 0 vector, the green vector here. Well, the green vector, it becomes 2, 0. So I multiplied it by 2. And so I just write 2, 0 as my first column. What about the orange vector? The orange vector, well, it flipped and it like decreased to 1/2. So it went from 0, 1 to 0, -1/2. So I write 0, -1/2 in the second column. So whatever happened to the 1, 0, I write as the first column. Whatever happened to the 0, 1, I write in the second column. So here we stretched horizontally by 2 because that was what happened to the green thing. And the orange thing, you can say compressed by a factor of 2. Let's be more specific, compressed vertically by 2. Or you could have said rescale. Wait, actually, let me continue. So you have to say compressed vertically by 2 and flip. Or you could just say rescale by -1/2. As long as you're mentioning the negative part, or the flip, and then the 2 part, which I just wrote instead by -1/2, because here I have compressed. Okay, there's also matrix projection. So you could project vertically onto a line or horizontally on a line. I'll do, I think I have an example later on, maybe. Yeah, so unless people have questions about this, I'll just move on to the example. Projection. Shearing is I guess I'll mention one thing also. Matrix projection. The determinant of a matrix projection matrix is always 0. Because you're like squishing things down. You're like projecting things down so that there's no like, what does the determinant of a matrix give you? Remember, it's either like the area or like the volume of the parallelepiped. So if the determinant is 0, that's because like we're shrinking everything down, we're squishing it. Whereas if we do a shearing, the determinant of a shearing matrix will always give you 1. Because you're not squishing anything down. All you're doing is you're kind of like shifting your perspective. You see how originally, if this is my standard basis vector, when I do a shearing, it just like moves the plane over a little bit. Okay. And I'll say that a property of matrix shearing is that usually one of the vectors stays the same. So like, for example, if I wanted to shear along the x-axis, that's this first vector here. Then the x-axis stays the same. That one doesn't change. I'm only moving the y-axis. So I want to see like this orange vector was originally 0, 1. And what does it move to? Let's say that this line is ax plus by equals 0, the purple line. Well, I know that my orange vector should still have the same y value of 1. It still has a y value of 1. So I just have to find what is x. Well, I plug 1 into my line equation. So ax plus b times 1 equals 0. And I try to solve for x. X is -b/a. So this point here is x equals -b/a, 1. So that's what I write in my second column. Okay, so if you shear along the x-axis, x-axis stays the same. If I shear along the y-axis will stay the same. Okay, and for rotation, just memorize what the matrix is. It's always cosine, sine, negative sine, cosine. Okay, I feel like we still have other volumes to get through, so I have a bunch of like examples throughout. Oh, and we still have change of basis. Okay, I'll let you guys look at those examples. Feel free to ask me questions if you have questions on those. Let me go to change of basis. So change of basis, remember that a basis is orthogonal if each of the basis pairs are orthogonal. So take each of the vectors in your basis, dot product them, and see if they all give you 0. If they do, it's orthogonal. Orthonormal has an additional condition where each of the vectors have to have unit length. So like here, if we have these two vectors and their basis, let's see, are they orthogonal or orthonormal? Well, u is written as 2, -4, right? Because I is just saying it's like the first component, and j is just saying it's the second component. V is 2, 1. When I do this dot product, I get 4 minus 4, which is 0. So yes, they're orthogonal. Orthogonal. Are they orthonormal? Let's see if their unit length, which is square root of 2 squared plus -4 squared, which is 4 plus 16. This is not 1. So we know that it's not orthonormal. Okay. We also have like change of bases questions. So do I have an example? Yes, let's do this example. Find the coefficients for x with respect to u and b. Right? And a lot of times these change of bases questions all boil down to an ax equals b problem. So keep that in mind. So they're saying, can I write x? Can I write 10 -3 with respect to, meaning like as some combination of u and b's? So can I write it as something times u, which is 2 -4, plus something times b, which is 2, 1? Is that possible? Well, let me also make these numbers like, I'll call them C1, C2. What's another way of rewriting this system? Well, I could write this as the first column, this is the second column, and I have C1, C2 equals 10, -3. Because notice that if I matrix multiplied this, what do I get? I get 2C1 plus 2C2, which is exactly the first row. And I get the same thing if I try to matrix multiply the second thing. I get the second row. So this is my ax equals b question. And here, let's look at A. A is a square matrix. It looks like it's invertible. So I can solve this by doing x equals A inverse B. What is the inverse of A? It's the determinant is this, minus -8, 1, 2, 4, -2. B is 10, -3. So this is 1 over 10 times 1, 4, -2, 2 times 10, -3. Okay, and I can keep simplifying this. Questions? Okay, I'm gonna move on to volume 2 then. Unless there's other questions on volume 1. After we get x, how do we find C1? Yes, so x is, if I solve this, I get, let me see, the answer will be like 16/10 and 34/10. And what was x? X was exactly C1, C2. So that means that this first number is C1 and this second number is C2. What does all of this mean conceptually? Like, what do the u and b coefficients mean? So here, u and b are acting like a basis. So usually we have like a standard basis. But like before we learn this class at all, we are always using the standard basis, which is 1, 0, 0, 1. Now they're saying like, can you write this vector, which we usually understand in our normal standard basis, but can you write it in terms of a different basis, which is this u and b? And the answer is yes, we can, because we were able to find a solution. We're able to write x. Okay, let me say x in the standard basis, right? This is our standard basis, is written as 10, -3. But x in this weird basis, capital B, where this weird basis is defined as ub, is written as 16/10, 34/10. Think of it like this is like inches and this is like centimeters or something. It's like a different way of writing things. So the way to write x in this weird basis is that in this weird basis, it's 16/10, 34/10. Yep. Okay. Let's move to volume 2. Okay. Volume 2. We have all the partial derivative stuff, Jacobian stuff, gradients, and Taylor series and critical points. Okay. Partial derivatives. Let's see. Partial derivatives, make sure you know how to take the partials. Let me do one example. If you have this function here, how do I take the partial with respect to u? Remember that all the other variables pretend they're constant, like pretend they're numbers. So this is like some number times u. The derivative of a number times u is that number. So it's this whole thing. And then over here, I have, remember, this is like some number. So that number stays there. And what is the partial of u to the negative 2? Well, that's negative 2u to the negative 3. Okay, and you can do all the other partials. We've done that a lot. So let me, oh, this is a good question, but we don't have time. Okay, but anyway, this is like how you find it. If you are given this weird matrix here, and you can find its determinant, you could find its sum, for example, and you create this function, which is defined as this. The important thing here to recognize is like, once you create this weird function, like what is the size of the determinant matrix? It's a 2 by 2 matrix because you have 2 outputs, 2 inputs. Okay. Rates of change in sensitivities. So once you have a derivative matrix, like now you can look at sensitivities and stuff. And also rates of change. So rates of change, this again kind of all boils down to an x equals b problem. Because sometimes they'll give you the matrix, like df, and they give you some rate of change of inputs, x bar. And they ask you what is the rate of change of outputs. So you solve and you get y bar, whatever. Other times they give you y bar, like the outputs, and they ask you to find the inputs. So they're asking you to find x dot. And that becomes the problem of what is x? Well, you could make it A inverse B, or you could do the row reduction stuff and back substitute. How do you know if a vector is a basis? So a basis is defined, the definition we know is like using linear independence. In math 2400, you'll also learn that it should also span your space, but I don't think we went over that, so that's okay. Just like linear independence. So if you have some basis, like 1, 2, 3, 4, 5, 6, whatever random numbers, you want to row reduce. And if you can get to the identity matrix, then that means that your vectors are linearly independent, and so they form a basis. So they're just row reduce and see if you get the identity matrix. If you don't, then that means that your vectors are not linearly independent, which means that one of the columns you can probably write as a multiple of the other column. So linear independent, like u and v linear independent means you can't write u equals something times v. And you can't write v equals something times u. They're like linearly independent, completely separate. Couldn't you verify the basis by finding the determinant and seeing if it is equal to 0? And how would you know you can't get an identity matrix? To see if you can get an identity matrix, try to row reduce it. If you can't row reduce it to an identity matrix, then you can't get to an identity matrix. The thing with the determinant, I think that's also true. You can see if the determinant of the matrix gives you 1. If it gives you 1, then you get a basis. If it's 0, then it shouldn't be a basis. Double check that on ed discussion. I think if it's 1, it's a basis. 1, then basis. And the reason is because, like, for example, the identity matrix or the standard basis that we know, that determinant is 1, right? So if other bases also give you a determinant of 1, that means that they're like, it's similar to the identity matrix. So it should also be a basis. Okay, let's see, rates of change. Do we need? Oh, I like this question. This question. Pretend you didn't see the answer. So consider a function whose derivative is this. At this point, the first output is not changing. What can you say about the rates of change of inputs? Okay, so we have this matrix here. And we're given a point, 2, -1. So let me plug in those points so that we have numbers. So I'm going to evaluate at x equals 2, y equals -1. And what do I get? Well, 2 times 2 times -1 is -4. X squared is 4. Negative y over x squared is 1/4. And this is 1/2. All right, so this is my derivative matrix. And they're saying that the first output is not changing. So I know that if I have this derivative matrix times some rate of change of inputs, I get a rate of change of outputs. My derivative matrix is -4, 1/4, 4, 1/2. I don't know what my inputs are, but I do know my first output is not changing. So not changing means it's 0. But I don't know what the second output is. They don't tell me. So this is what I know so far. And they ask, what can I say about the input rates of change? What can I say about these question marks? The first thing I want to try to do is like, well, I don't have a number here, so I can't really solve for anything yet. Let me try like multiplying this out and see what I get. So I know that this is some like inputs. Let me call them x1, x2, right? So if I matrix multiply, I have -4x2, x1 plus 4x2. And here I have 1/4 x1 plus 1/2 x2 equals 0 and something I don't know. Well, the first row, what does that tell me? It says -4x1 plus 4x2 has to equal 0. Or what if I simplify and add 4x1 to both sides and then divide by 4? So this tells me that the first input and the first output and the second input, the first input and the second input have to be the same. So x has to change at the same rate of y. Oh, I guess they called them x and y. But yeah, first inputs and second outputs all have to be changing at the same rate. Questions? Okay, we have some differentiation rules. Chain rule. Chain rule, just remember the formula for it. The derivative of some composition at a point A equals, and this is the important part, this has to be evaluated at G of A, and this has to be evaluated at A. So you can remember the chain rule. Here I have the branch diagram way of remembering what the chain rule is. Sometimes this is helpful in the case of like if they ask for some random partial derivative, it's important to kind of visualize things. So here I have an example, right? Let's say W is given like this, xy plus z. So W is a function of 3 variables. Let me start. W is a function of 3 variables, x, y, and z. And they tell me that x, y, z equals cosine t, sine t, and t. So that means that each of these variables are functions of t. So they all depend on t. Then I get this tree diagram thing. And each of these lines, you write them as like the partial of the upper variable over partial of the lower variable. This is partial x, partial t. This is wy, yt, wz, and zt. So if they ask me to find the partial of w with respect to t, I have to make sure that I look at all paths. What are all the ways that I can get from w to t? Well, there's 3 ways. There's this first way, the first path. So I multiply like each of the branches, partial x with partial w with partial x, and partial x partial t. There's also this way, that's this path. And there's also this way, that's this path. So I have to add them all up together. So this is a way of recognizing, like, making sure you're not missing any components when you try to do the chain rule. Okay, here I have a proof of why you get the same answer, and like why things in between work the way they work. Okay, we can skip that. Let's go to inverse function theorem. All right. The main thing to know about inverse function theorem is, what does it even say? It says f is invertible if its derivative is also invertible. If that's true, that's why we get this equality. Instead of like finding the inverse first and then taking the derivative, we can take the derivative first and then take the inverse. Why is this even useful to us? Because like if we find the derivative first, well, we have all those like matrix techniques to try to find the inverse, right? We have like the 2x2 matrix, we have a formula. If it's a bigger matrix, we can like do the row reduction stuff. So this is like much nicer to compute, as opposed to like here, if you're forced to find the inverse first, then you have all these like variables and stuff, and then you have to take the derivative, like it gets confusing. So that's why this function is useful. Let's see. So say we have this example. We're given these functions. F has inputs of u, v, w, and outputs of s and t. G has inputs of x and y and outputs of a, b, c. And they say, what are the input and outputs of the composition? So this question is asking you, like, do you understand what a composition is? What is f of g doing? Well, let's start at g. G takes in x and y. It does whatever it wants, and it outputs three things, A, B, C, three things. Then F can take in those three things. It doesn't matter that these are like different letters. They're just like labels of how I labeled them. But we have three things, and F takes in three things, and it outputs two things, S and T. And so in total, the outputs of this composition are two things, S and T, and the inputs are two things, X and Y. So this helps me verify that if I wanted to find the derivative of the composition, it should definitely be a 2x2 matrix because I have two inputs and two outputs. Questions on that? And then what is let's see, what should I do? Okay. This question says, is the composition of f of g locally invertible where all the inputs equal 2? Well, let's suppose that there were actual like numbers here and I was able to compute the derivative and I end up getting that the determinant is 0. That means that the inverse function theorem is, we can't say if it's invertible or not. The inverse function theorem is inconclusive here because we got a determinant of 0. You can't say that it's not invertible. We don't know that for sure. All we can say about the inverse function theorem is that if I had gotten the derivative is not 0, like some number, then I can say it is invertible. But if I get 0, I can't really say anything about it. Okay, then I have this question from quiz 6. And I think this was a common question that people had. So in this question, they gave you two like things. They said x is a function of u and v. So two inputs, u and v, and you get out this thing. Y, you also put in two inputs and you get out this thing. And let me just call this my function f. It has two inputs, which are u and v, and it has two outputs, which are x and y. Okay. Let's see. So, I probably shouldn't have. Oh, okay, I see. I should have been in the template one. Anyway. Okay, here. So can we write u and v as functions? The first question is, can we write u and v as functions of x and y? So right now my function f, it has inputs of u and v and outputs of x and y. That's what's given in the problem. Part A is asking, can I switch them? Can I can I find like some function, I'll call it g, such that the outputs are u and v? Or sorry, the outputs are, yeah, u and v, and the inputs are x and y. So can I write u and v as functions of x and y? Functions of those variables, those are the inputs. All right. And notice how like my inputs and outputs switch. Like originally f has this, g has the opposite. So the fact that it's like opposite makes you want to think of like an inverse. So we want to look at the inverse function theorem. Remember the inverse function theorem, what did it say? It said, in this context, f is invertible if its derivative is invertible. So I should find df, right? What is df? df is going to be, right now my outputs are x and y, my inputs are u and v. So outputs are the rows, right? And inputs are the columns. U as the first column, v as the second column. So if I find this derivative matrix, I get 2u, 3v squared, v u e u v plus 2. And what am I evaluating at? U is 0, v is 1. So when I plug in 0, 1, I get 0, 1, 3, 2. This determinant is 0 minus 3, which is -3. That's not 0. So the answer is yes. I can write u and v as functions of x and y because I can find an inverse by the inverse function theorem. By the inverse function theorem, I found that df is invertible, and so inverse is good. All right, part B said find partial u, partial y. Well, notice in F, we don't have partial u, partial y, but like notice that I have y over u, but that's kind of like switched. That's another sign, like things are being opposite. Things should be like the inverse. So this question is asking us, let's try to find g, or like the derivative of g. Because what is g? G has outputs of u and v and inputs of x and y. And so if I find dg, what does that give me? My outputs are the rows, remember? And inputs are the columns. Okay, so if I find dg, I can find my answer. Here's partial u, partial y. Okay, well, what is dg? That's the question, dg. Well, I defined the g as the inverse of f. That's what I called it. Because g is inverse of f. So I can write d f inverse. Then, what is this equal to? By the inverse function theorem, we said that f is invertible. If f is invertible, we have this equality that df inverse equals df all inverse. So I can say that this is df all inverse by the inverse function theorem. And in part A, I already found what df is. It's 0, 1, 3, 2. So all I have to do is find the inverse of that, which I get -2/3, 1/3, 1, 0. So that means that this partial of u with respect to y is 1. Questions? Okay. Let's look at the second question also. I feel like this was a good question. So they said that you're given these two things. You're given that dh equals that thing, and dz equals that thing. The first question is, you want to use this information to compute h of z. And you want to conclude that it's invertible. If you want to conclude that it's invertible, like, what do you need to know? Well, first of all, let's look. What do you need in order to conclude that h of z is invertible? Well, by the inverse function theorem, IFT, h of z is invertible if the derivative is invertible too, right? Okay. But to even determine if this is invertible or not, we have to actually find it first, right? We have to know that this exists. Does it even exist? Can we find this derivative in the first place? Like if we can't even find it, then how are we supposed to take the determinant of it? So first I have to know it exists. How does it exist? Well, how do I find it? I have to use the chain rule, which says that this is equivalent to dh at z of a times dza. So does it even exist? By the chain rule, if this exists, then sure it exists. Now, is it possible to do the chain rule though? The important part is that, are these values actually accurate? Like, is 1, 2, 3, if 1, 2, 3 is a, is z of a equal to 0, 0? That's our question. Because if z of a is not 0, 0, then how am I supposed to do this multiplication? I don't know what dh is. And so the answer here is that you need to know z of 1, 2, 3 equals 0, 0. Okay, and part B was, can you draw the conclusion that it's invertible? Well, assuming now that we are allowed to do this matrix multiplication due to the chain rule, h of z is invertible if the derivative is invertible. So let's find the derivative. If I have this equality here, then dh of 0, 0 is this matrix. dz of 1, 2, 3, 1, 2, 3 is this matrix. I do this matrix multiplication, which is like a 3 by 3 matrix. I'll just write all the numbers here. And I find its determinant. What is the determinant? I get 2 minus negative 13. Minus negative 3, I'm expanding on the first row. 20 minus 26. Actually, because in my notes, I expand on the first column. So let me do minus 10, negative 6 minus negative 1, plus 2, negative 39 minus 1. And we get 0. So this derivative matrix was not invertible. And so the answer is we cannot conclude that it's invertible. We can't say anything. Can you go back up just to see the partial of u with respect to y? Yes. Oh, sorry, that was like 2 minutes ago. But yeah, this. Okay, questions so far? Okay, and remember this was this question. So this required chain rule and inverse function theorem. All right, what about gradients? Let's move on to gradients. All right, what is a gradient? Gradient is where we have a function that's written like one line, like something, like an implicit thing, which means that we only have one output. So it's like a smaller version of the derivative matrix. Or another thing to remember is that the gradient is a vector, like one column, whereas df, the derivative matrix, is a matrix. So that's the difference. And similar to how we always have that ax equal b problem, ax equals to b, with the derivative matrix, we could also do the same thing, but with the gradient, where we have the gradient times some input vector equals some output vector. So they're the same thing in different, actually, let me not say that. I'll just say that both allow us to input some rate of change of inputs and output some rate of change of outputs. Okay, and yeah, I said that the difference is that one is a matrix or linear transformation, and the gradient is only a vector. Okay, let me go to level sets. Level sets, how do we find level sets? Let me do an example, which is this one. I like this example. So here we have this function, which has two inputs, x and y. And we're saying that this is a level set, and we're saying like, what are the level sets? How do I find level sets? what you do is you take that equation, x squared plus y squared, that x squared plus y squared, and I set it equal to different numbers. For example, I could set it equal to 1. What is this a picture of? Well, it's the equation of a circle of radius 1. I could set it to other numbers. I could say it's like 4. Then I get a circle of radius 2. I could keep doing this and I get these circles. So the level sets of this function are circles, specifically level curves, because they're like curves. And I'll note that if you actually like drew this out on GeoGebra, like in 3D, what it looks like is this paraboloid. So the fact that here we have 2 inputs, right? We're living in 2D space. The level curves are also in 2D, but the graph lives in a dimension higher, lives in 3D. Can we think of the derivative and the gradient as transpose of each other? I would be careful with that because what if the derivative matrix is 1, 2, 3, 4? Then what is the transpose of that? The transpose is 1, 2, 3, 4. But we know that the gradient can only be a vector. It can only be like a column thingy. So it's not always the transpose of the derivative. Okay, so that was this question. Now let's see if I have the same function, x squared plus y squared, right? But now I'm telling you that I am using 3 inputs. I'm living in 3D, 3 inputs. What is the difference? How do I find the level sets? So remember, I take my function and I set it equal to numbers. I could set it equal to like 2, or let me do 1, for example. What is x squared plus, and remember, we're living in 3D right now. So what is this equation in 3D? That's the equation of a cylinder of radius 1. I know it's a cylinder because if I'm in 3D, this equation only uses x and y's. I don't have any z's at all. So z could be anything. Z could be 5 and I have a circle of radius 1. Z could be 0 and I have a circle of radius 1. So like I have like circles at each cutout of z, and so that gives me the cylinder. What about the level set at like 2 or 4 or something? Then that gives me a cylinder of radius 4, and so on. So my level sets are cylinders or level surfaces because they're like 3D things. So surface, these cylinders in 3D. So the level sets are in 3D again. But if you drew this out, you'd actually get something in 4D, which we can't really picture. So I didn't draw it. But yeah, this kind of tells you the importance of realizing what space you're living in. Because see how both these equations were x squared plus y squared? But the fact that this lived in 2D and the fact that this lived in 3D, you got different level sets. Okay, and the thing to know about gradients, the relationship between gradients and level sets is that they're always perpendicular or orthogonal to each other, I mean. Questions so far? Okay, what about tangent spaces? Let's see. We can find an implicit equation of a tangent space. We could also find a parametric one. Let me start with implicit. Implicit means it's like written as one thing, like one thing equals 0. So let's say we try to find an implicit equation for the tangent plane at this point to some paraboloid. So we have some paraboloid. We want to find the tangent plane, this plane, and it goes through this point, 1, 2, 4. Well, if I know my plane, or my paraboloid, sorry, is this thing, x squared plus y squared plus z equals 9, what do I know? And I want to find, okay, so what am I trying to find? I'm trying to find what is the equation of the plane, the purple plane. How do I write any equation of a plane? I always need the normal vector, right? So I need this purple vector. The normal vector you can kind of think of as like some gradient thing. And so what do we know about the gradient? It's always orthogonal to the level set. So that will give me like the level set, this like plane thingy. Okay, so let's see. I have my paraboloid, which I'm gonna write as x squared plus y squared plus z minus 9. I got that from my paraboloid equation. I'm gonna take the gradient of the paraboloid. The gradient gives me 2x, 2y, 1. And we have this point, right? So I can plug in my point. The gradient at the point 1, 2, 4 is 2, 4, 1. So this is my gradient. That's like the normal vector that I wanted. But I want the equation of the whole plane. So how do I do that? Well, I use the equation that I wrote here. Gradient times x minus a. That means that I do gradient, which is 2, 4, 1, dot with whatever variables I have. The variables I have are x, y, z, right? Minus the point I have, the initial point, which is 1, 2, 4, equals 0. So this goes back to like the very beginning of this review session where like how was I writing an equation of a plane? This is 2x minus 1 plus 4y minus 2 plus z minus 4 equals 0. And I can simplify it to get 2x plus 4y plus z equals 14. So this is the tangent plane that lives in R3. This is the implicit equation. Question in the chat. So to summarize level sets, in that case, were all the possibilities of x squared plus y squared equals NEC? Yes, exactly. So all the level curves here, all the level sets are x squared plus y squared equals all the possible numbers in C. Same thing over here. That's how you get the level set. Sometimes they say like, what is the level set at a certain value? Then it's just like that one circle or that one cylinder. But in general, all possibilities are, you set it equal to everything. Or anything possible, I mean. Okay, so that was implicit equation. Questions? Okay, we could also do a parametric equation. So here we see that we're trying to find a parametric equation for the tangent plane at this point to some surface. So what is the surface that we're considering? We're considering this surface. And let's see, what should I try to do? First of all, in the previous example, we found the gradient of my paraboloid thing. But now notice that I have 2 inputs and like 3 outputs now. Over here, I just had one implicit equation. So here, because I have multiple outputs, I have to find the derivative instead of the gradient. You can only find the gradient if you have one output only. That's why the gradient is always like an n by 1 vector, because there's only one output. Okay. Anyway, let's find dr. So dr is going to be the partial of r with respect to t1 and the partial of r with respect to t2. So what do I get? I get 1, 3 t2, negative 2 t1, negative 2, 3 t1, and 1. But I need to evaluate this at some point, t1, t2. That way I can get numbers for my derivative matrix. So what are t1 and t2? Well, all I know is that like this 192 point exists on this surface. So I know that 192 exists on the surface, and I can use that to try to solve for what is t1 and t2. So here you would have to kind of slightly guess and check-ish. I would say start with like the easy numbers and say, what if t2 equals like 1 or something? If t2 equals 1, t2 equals 1, t1 has to equal 3, so that I could get 9. And let me check, does 3 minus 2 equal 1? Yes. And I can check 1 minus 9. 1 minus 9 is negative 8 plus 10 is 2. Yeah, correct. So this is my t1 and t2. And I can plug these in to my derivative matrix to get actual numbers. Okay, so how do I write the parametric equation? I have my initial point. R at the point was 192 plus my variables. Notice I have two columns, so I have two variables. I should have S times the first column. Let me write it as this thing, plus T times the second column. In other words, 192 plus S times the first column. That was over here. And the second column is this negative 291. Okay, questions? And these two vectors are tangent to my surface. Actually, I might have an example of that later, but yeah. Okay. Oh, here's the example I was talking about later. It's now. Okay, consider the parameterized surface in 3D given by this. And they ask you to find the derivative matrix, which I trust you guys to do that, but I'll put the answer here. This is the derivative matrix, just so that we can use it. All right. And the question says, find a pair of non-zero vectors tangent to the parameterized surface at some point. Okay, so we have some surface in 3D, right? Some random surface. And we're trying to find the non-zero vectors tangent to it. So I want to find like this one, and I want to find like this one. Imagine they're all living in this plane. I want to find those two vectors that are tangent. By finding this derivative matrix, each of the columns are going to be the tangent vectors. Why do I need two columns? Like, why do I need two vectors to represent a why are these two vectors tangent? Think about like how we represent a plane. Whenever we write an equation of a plane, or even in like a normal graph, like an XY plane, right? In order to write any point over here, like 1, 5, I need some X component and I need some Y component. So in the XY plane, I need two things to describe any point. So using a similar idea for any plane, I need like two tangent vectors. I need like this vector and this vector. They like make up, they can describe my plane. And so if I just take these two columns, they're going to be the vectors tangent to my parameterized surface. So I do df, evaluate it at the point 1, -1, 0, and I get 3, -3, 2, 1, 2, -2. So the pair of vectors tangent are 3, -3, 2, and 1, 2, -2. These are the tangent ones when I take the derivative. Just like how if I were given like a path and I take the derivative of it, that gives me the tangent vector, right? Tangent always has to do with like derivative. Okay, and part C says find a normal vector to the tangent plane at this surface. Well, I need to find this, or I need a normal vector. So I need like this purple vector. How do I find this purple vector? Remember cross product. Cross product of two of these like tangent vectors always gives us the vector that's sticking out. So if I do the cross product of 3, -3, 2, cross product with 1, 2, -2, I will get 289. So that's the answer here, 289. Questions so far? Could you also find where the dot product is 0? Could you also find where the dot product? Yes, it would have, you would have to, it might require like some guessing and checking though. Like you would have to make sure the purple times one of the tangent vectors is 0 and that it times the other tangent vector is also 0. It has to be, the dot product has to be 0 for both. You can't just do one. It's like let's call this U, V, and W. U dot V has to equal 0 and U dot W has to equal 0. What did you plug in for SNT? SNT. Oh, I see. Yes, thank you for checking that. You have to find SNT to plug in. So turns out that SNT of one works, and this kind of required the guessing and checking thing again, because I know that this point exists on my parameterized surface, and my parameterized surface was given by this. So I know that this equals, for some SNT, it equals 1, -1, 0. And so I need to solve for SNT, and I just guessed, like, what if S equals 1 and T equals 1? Then 1 cubed times 1 is 1. 1 minus 3 turns out to be -1, and 1 minus 1 is 0, so perfect. Yeah, and that brings up another important point. Always make sure, like, if I had written like 1, -1, 0, it wouldn't have made sense, because that means that there's 3 inputs, but my derivative matrix only had 2 variables, so that doesn't make sense. So always make sure your like dimensions are matching up and stuff. Okay, let's move on to linearization. So we're gonna get into all the Taylor series stuff soon. All right. Let's see. Linearization, I kind of like generalized to different types of problems that show up, but maybe it might be more helpful to, I'll mention the main points. Okay. One type is trying to estimate something, like something really hard. Like say I want to estimate square root of 3.56 or something. Yeah, something like that. Then what do? I have to like, it's approximately equivalent to the square root of something close, like a nicer number, like 4, right? So this x naught, y naught is like some nicer number, 4. But that's not exactly equal to 3.56, right? There's some like extra error part plus this error. So this error part, how do I find it? Well, the error part is equal to df. df. Error is equal to df. What is df? df is each of the partials, but after each of the partials, you write this like dx thing. So partial with respect to x dx, partial with respect to y dy, partial with respect to z dz. This is the error term. So whenever you're estimating something hard, it's always going to be equal to like the easy thing, something that's easy, plus your error term, which is df. And in terms of how, if they want, okay, so those were like, that's the linearization part, estimating things. What about the errors part? So sometimes they ask you to find the amount of error of a variable. Like say they say the radius varies by 0.03. Estimate the value for the resulting change in volume, V. If they ask you for the change of something, that's just asking you to find D of that variable. Like change of volume, dV, change of area, dA, whatever. But if they ask you for a percent, so they say like the radius varies by 10%, find the percent of error. Percent always means that they're asking you to find the variable over that variable. So like percent of change in volume, dV over V. Percent change in density, D or like area, dA over A. So that's like, which version do you want? Do you want just the D variable one or the D variable over variable one? Then you have signed versus not signed. In the case where they ask you for like a change of something and they say the radius is off by positive 0.03, then that means that they want you to use signs. Like they want you to, like if you end up getting dr plus dx or something, and dx is like negative 0.03 and dr is positive 0.03, then it turns out that the error is 0 or something. So they want you to use like whatever plus and minus is there. But if they give you an absolute value, that means they want you to find what's the most possible error you can have. So you don't care about the signs. You want everything to be as large as possible. So then you might say like dv equals dr plus dx, which would be 0.03 plus absolute value of negative 0.03, which gives you 0.06, right? That's the largest possible error you could have. That's where they give you like numbers. If they give you the percent version, there's a similar type, right? If they want you to find the absolute value ones, just make sure that you always take the absolute value. You want like the biggest error you can possibly get. So that was my summary. We can do an example problem. Let me see if let's do, okay. Let's vote. Do you want a estimating problem or error problem? Estimating problem, thumbs up. Error problem, do a heart or something. Okay, I see lots of. Okay, I see a mix of both. Okay, I'll just do both then. All right, so the first one is error one. All right, so we're given this function. It says compute the differential df. So remember, what is df? It's each of the partials with the d stuff, right? The error. So how many variables do I have? I have 3 variables, x, y, z. So that means that df, just by definition, is the partial with respect to x dx plus the partial with respect to y dy plus the partial with respect to z dz. Okay, so I have my formula down. Now I can take the partials. So here I rewrote my function as the z -1 just so that I can take the derivatives much easier. Okay, so how do I take the partial with respect to x? The 3 comes down, so I have 6x squared, y squared, z inverse dx. Partial with respect to y is 2. Oh, wait. Partial with respect to y. Okay. Is 4x cubed y over z dy. And partial with respect to z is minus z to the -2. So I put that minus down and -1 becomes -2 dz. All right, so I have 6x squared y squared over z dx plus 4x cubed yz dy minus 2 of this dz. So this is my df. Part B, compute and simplify the relative rate of change. So notice that it's like relative rate, or they could have said like percent rate of change of f. If they use that wording, that means that, see, they want you to find df over f. The differential was just df, but the relative rate of change, it has the dividing f. Okay. And the whole point of dividing by f, as you'll see, the whole point is that a bunch of things should cancel out. So if things don't really cancel out, that's a sign that maybe something messed up in your calculations. But let's see, what is f? 2x cubed y squared z. All right, what do I mean by canceling? Let's look at this first term. When I do this divided by this, I multiply by the reciprocal. So I multiply by z over 2x cubed y squared. See that the z cancels, the y squared cancels, one of the x cancels, and the coefficient becomes a 3. So we get a 3 over x dx. Okay, we can keep doing it. Let's do it with the y terms. We'll get 2 over y dy. Let's do it with the z terms. 2's cancel out, x's all cancel out. We're only left with a z in the bottom, dz. Okay, so this is 3 dx over x plus 2 dy over y. And I'll say why am I writing it as d variable over variable? It's because we're going to use that in part 3. So usually you should end up with like a number with these relative rates. That's a sign that something went well. Okay, part C. If the value of x can vary by plus minus 1, value of y can vary by plus minus 2, z plus minus 3, then what percentage can f vary? So first thing I notice is that they give me this plus minus choice. So they're saying like, and they only say like, what percentage can it vary, like in general. So they want like the biggest percentage that it can vary. Okay, so that means that I want the absolute value version. Like what's the biggest it could be? What's the most change it could be? So I want the absolute value of df over f. Okay, so that's going to be 3 dx over x plus 2 dy over y. And when I take the absolute value, remember I want the biggest change. So I can add 1 dz over dz. Okay, and the fact that like these being written in percentages already tells me that dx itself over x is 1 absolute value. Okay, because it's a percent, remember a percent means that it's d variable over variable. This is dy over y equals 2, and this is dz over z equals 3. So I can plug those in. I have 3 times 1 plus 2 times 2 plus 1 times 3. So that's 10. Questions? Okay, then the estimation question. All right, so part A says, let's pretend they didn't even tell us these parts, right? Or I guess I need this information, but let's just say they told me to estimate f of this. So pretend you didn't even see these parts. Like, how are you supposed to know what to do? Remember that I said the hard number, so f at this thing, equals, well, if I'm trying to estimate something, I could probably get as close as possible as I want to it. So I can say that it's equal to some nice point, right? And notice that 3 is closest to this number, 9 is closest to this number, 2 is closest to this number, plus some like error, some error thing, df. Okay, so what is f evaluated at 392? This is my f function. F at 392 is 4 times x squared over square root y times z squared, which is 3. This is 3 plus df. What is df? Remember from the previous problem that df is all of the partials with the like the d thing. So this plus this plus this. Okay. What is the partial with respect to x of this thing? It is 8. I'll just give you guys the simplified version. It's this plus actually minus 2x squared this dy minus this dz. Oh wait, yeah. Okay. So, and all right. So that's df. But notice that it's like not a number, right? What do I do with that? So I need a number to plug into like these values, these x, y, z's. So let me write down, what are our hard numbers? Hard numbers are for x, y, and z. The hard numbers are 3.1, 8.7, 2.2. The easy numbers are 3, 9, and 2. Well, I don't really want to do things in the hard way, right? Notice how f was evaluated at the easy point. So df should also be at the nice point. Maybe I shouldn't call it easy. I should call it nice, not easy. Nice. So what is df at the nice point? 3, 9, 2. Well, 8 times 3 is 24. divided by 3 times 4, divided by 12, so that gives me 2 dx. And I plug these points into here, and I get minus 160y, and I plug them in there, and I get 3 dc. So df at the nice point is this. So far I have 3 plus df at 392, which is 3 plus this thing. What are the dx, dy, dz? You want to think of every time you see a d variable, think of change of that variable, change in that variable. So what is the change in x? Well, that's always going to be the hard number minus the nice number. That's 3.1 minus 3, or 0.1. 0.1. And then dy, change in y, is going to be 8.7 minus 9, which is negative 0.3. Negative 0.3. And then dz is the change in z, which is 0.2. Okay, and now you can simplify and get 2.65. Okay, so the things to remember, f of the hard thing equals f of the easy thing plus df at the easy thing, or the nice thing, sorry. And when you get the df, what are the d variables? Those are the change in those variables. Change in those variables are hard minus nice. And you can solve. I missed the first part. Where did the 3 come from that is being added to df? Right. 3 is f evaluated at your nice point. Because like whenever, like say we wanted to evaluate square root of 3.9, like how do I do that? It's probably approximately equal to the square root of 4 with some error to it, right? Square root 3.9 is close to square root 4. So I chose like a nicer number here. So same thing here. We have this hard number, but I chose a nicer number. So this value is close to 3, but there's some like error term. And the nice numbers I just choose because whatever is closest to like being whole numbers, and then I plug in 392 into my original function to get 3. Cool. Okay, other questions? Okay. Let's go on to Taylor series. Okay, Taylor series, what are things to know? Taylor series, this notation thing sometimes is good to know. So if you're given this capital I of these numbers, what does that mean? Like di of f. That means that like you look at which variables correspond to which number. So x corresponds to 1, so I should do a partial with respect to x once, partial with respect to y no times, partial with respect to u 2 times, and partial with respect to v 1 time. So if I say d of 1, 0, 2, 1, that means I should do the partial x, or sorry, I should write it like this. This is, in total, how many partials are we taking? 2, 3, 4 times. We're taking a partial 4 times. So partial 4 times. I have x once, u twice, and v once. This is the same as this notation. And I'll note that the order doesn't matter. So if you wanted to take the partial with respect to v first, and then u twice, and then x, you could do that. Or you could also like say one variable is like easier to take the partial with respect to first. Maybe I want to do x first, and then maybe I'll do v, and then I'll do u squared. It doesn't matter. They all give you the same answer. Okay. Taylor series, don't forget what those common like Taylor series are, like sine, cosine, e to the x, natural log, and 1 over 1 minus x, or 1 over 1 plus x. Could you show us the answer to the problem above? Oh yeah, this partial. So this partial is, so I said it's equal to this, and I say that the order doesn't matter because taking the partial with respect to one of the variables is probably a little bit easier, maybe. Maybe it doesn't matter, but yeah, okay, so let's do this. So we want, I put the u's on the outside, and then the v, and then the u. Okay, and this is my function here. So I'm gonna do u first, and then v, and then u squared. Or sorry, sorry, I wanna do x first. You can try it out as an exercise to do it different order if you want and see if you get the same answer. All right, so when I do the partial with respect to x first, what do I get? Here, you see that there's an x here and there's an x here. So that means that I'm multiplying two like x terms. So I need to use the product rule for this. So I can choose this as like one of the terms, this as the other terms. What does product rule say? I do the first term times the derivative of the second term plus the second term times the derivative of the first term, which is 3x squared uv squared, like that. And there's no x term over here, so that's it. So that's the partial with respect to x. Now I take the partial with respect to v. What do I get? There's a, let me write this as, I'll just write it as u squared v squared, so that we're not confused. All right, so I get 2x cubed u squared v y xy, because there's only one v there. Is there a v over here? Yes, also over here. So this is plus 6 e to the xy x squared u squared v. And then finally, I'm going to take the partial with respect to u of this one time to get 4x cubed u v y e to the x, that. And also partial with respect to u over here is 12, like this. And one more time, to get 4x cubed vy e to the xy plus 12 e to the xy for v. Okay, and that's it. That's the answer. Questions? All right, Taylor series. Test out this example. Some of, if people are doing like the calc, never mind, I won't say it. Okay. Yeah, let's look, because we're running out of time. So you can look at the answer to this in the notes on my website. Let me find another example that I think will be more beneficial. I'll mention this one from the quiz question, right? Like if you're given this Taylor expansion like this, and they ask you, what is this? Partial. Remember the notation. This is telling me that I take the partial of x 3 times and y twice. So my choice of I is 3, 2, where 3 corresponds to x, y corresponds to 2. And in my Taylor series, how do I write the Taylor series? Like each of these terms are written as 1 over I factorial di f xi. Where this here, if I is 3, 2, what is 1 over I equal to? 1 over 3, 2 factorial is each term, like I take the factorial of each term. The 3 factorial, 2 factorial, which is 3 times 2 times 2. So that is 12. All right, and what is this DIF? That's the same as writing the partial of f with respect to x 3 times, y 2 times. And what does this xi mean? It means whatever variables I have to the I-th power. So that means that if I'm doing x 3 times, it should be x cubed, and y is twice, y squared. So this term is wherever I see, do I see an x cubed y squared term in my Taylor series? I do. It's this. So this equals to 2x cubed y squared. So if that's the case, I found that 1 over I factorial is, sorry, they should all be like 1 over. 1 over 12 partial like this of x cubed y squared. I found the term in my Taylor series. It should be equal to negative 2x cubed y squared. And so now I start canceling things out. X cubes cancel out, y squared cancel out. So that means that this partial equals negative 2 times 12, which is negative 24. So the things to know were, can you recognize what this notation means? Can you find that respective term? And can you solve, like you didn't forget the coefficient here? All right, questions on that? All right, critical points, let's see, critical points. Critical points are kind of like in single variable calc where the derivative, or in this case now the gradient equals 0. The Hessian matrix allows you to classify critical points. So the second derivative test, what does it do? I want to find the Hessian matrix, which is found by taking the derivative matrix twice. And if the determinant is greater than 0, that means I have a local extremum. So I have to look at the sign of the determinant and the sign of the trace to see if it's a max or min. If the determinant is less than 0, it's a saddle point. If the determinant equals 0, test is inconclusive. We don't know how to classify the point. Okay, so here we have this example from the quiz. They say that we have a critical point, or like you're given this Taylor, actually you're not given a Taylor series. You're just given this function and you're told that it has a critical point at the origin and you're told to classify it. The first thing that comes to mind is maybe take the derivative, find the Hessian, do the determinant. But you see that this is very complicated. Like if you wanted to take the derivative of this thing, you have to do multiple product rules, which you don't really want to do, right? So that's a sign that maybe we should use a Taylor series expansion. Because the Taylor series expansion is just another way of like rewriting the equation. Let's find the Taylor series. So e to the x plus y, what is that going to be? Recall that Taylor series of e to the smiley face is 1 plus smiley face squared, so on. That means x plus y will be 1 plus x plus y squared, so on. What is sine of smiley face? Sine is the odd one, so you have smiley face minus smiley face cubed, so on. So that means that sine of x squared minus y squared equals that x squared minus y squared minus the smiley face cubed over 3, so on. And then cosine is the even ones. So I start at 1 minus xy. Oh, sorry, this is just xy. xy all squared over 2, so on. All right, so g of x, y, you're like, it's each of these things multiplied, right? So you would want to like FOIL every single thing. But once we FOIL things, a lot of the higher order terms, like they don't really matter to us. They're just like extra stuff. All we really care about, like what's most important is what is the highest degree term that matters to us. Like that represents our entire function. So you just want to take the lowest term from each thing and multiply them. So we get x squared minus y squared. And there's a bunch of like other higher order terms. But we just really care about like what's the main thing that is able to represent all 3 of these functions. Okay. And so we care about this first term. And now we want to look at the behavior of this. What's happening? What is happening as x increases? As x increases and gets really large, like say my y is constant. As x increases, I get some huge number. It keeps increasing and increasing. I get some huge number minus y squared, right? So it's getting bigger and bigger and bigger. As x decreases, like when I plug in negative numbers, a negative number squared is still positive. So as I get even more negative, x squared still gets bigger. Right, so I still get a huge number, minus y squared, so still positive. All right, what happens as y increases? Well, I have x squared minus y squared. It keeps getting bigger and bigger and bigger. So minus some huge number. So it could become a negative number. Because I could have like 2 minus 2 is 0. But then as y increases, 2 minus 4 is negative 2. 2 minus 5 is negative 3, so on and so on. So it keeps getting negative. And same thing when y decreases. You keep getting a huge number, so it's negative. Right? Because even if we plug in a negative number squared is positive. So in the x direction here, if it keeps getting bigger, our values keep getting bigger, that kind of looks like a min, right? Our values keep getting larger and larger and larger. Over here, the y behavior, our numbers keep getting smaller and smaller and smaller. Like as y increases, we get negative. As y decreases, we get negatives. This is like a max. So in one direction, we have a min, other direction, we have a max. Different directions, we got different things. That's what a saddle means. Saddle means that in one direction, you have one behavior, in the other direction, you have a different behavior. Okay, so that was this problem. Questions? I'll note that in some examples of the quiz, pretend like this cosine x, this was like an x here or something. Pretend our function was composed of these three things. Some people just foiled the first two terms and said that x squared minus y squared is like the thing we should look at. But if you only multiply these two things, you're only taking into account the e part and the sine part. You didn't include the cosine part. So you would have to still multiply by this another x. You have to like take into account all parts of your function. How do we know that we only need x squared minus y squared term and not all the others? Right, because okay, let me bring this back to what it originally was. This was a 1. Like if we try to FOIL out everything else, like we just get a bunch of like higher order terms. Think of them as like redundant, kind of redundant information. Like you could write it as big O of something. So we just really care about like the smallest degree thing that gives us like the global behavior. Let me think if there's another way to explain. Yeah, just look at the lowest degree terms. Can you go back to the answer from the I problem? Yes. The I problem was this one. X 3 times, Y 2 times, so 3, 2. Other questions? Okay, good to move on from the I one. Okay. And again, all the notes will be posted after this session. Okay, let's go into constrained optimization and the Lagrange stuff. So let's say you're given this graph, right? Sometimes you're given graphs of things and they wanted you to find like, is this a min or a max? How do you determine if it's a min or max? So in this question, we have these level sets. This is a graph of a level set. And they're telling you that we're constrained on some line. Like this line is our constraint. And they want you to see like, is this critical point a max or min? Well, what you wanna do is imagine walking on the constraint. Like imagine you're a person walking on the constraint line. When you're over here, you get to this first level set. This is the level set of 0.02 over x. So that's like a small value, right? You're at a lower level set. As you keep walking along the line, you get to this level set, which is 0.5. So you got to like a higher point, right? But then when you keep walking along the line, you get back to that lower level set, the 0.02 one. So you went back down. What does this look like? It's a max. That means that based on this picture, this critical point is a maximum. Okay. Yeah, questions? All right. For constraint problems, how do you like find what they are, or like what the critical, or like how do you find the critical points? You have to use Lagrange. So what is Lagrange? And also as a note, I don't think we went over how to classify critical points if we're in Lagrange, so don't worry about that. We only know how to classify points for the non-constrained problems, and that's using the Hessian matrix. All right, Lagrange. How does Lagrange work? We have a function f, and we have a constraint g, and the equation you want to make is gradient of f equals lambda gradient g. All right, so here I have an example problem. So let's say that you have a factory, and this is from spring 2017 final. Let's say you have a factory full of robots, and that make pizzas. Assume you have x greater than 0 robots. Each robot can be used to produce per hour. First question, what is the total number of pizzas produced per hour? Okay, think about this. We have robots that make pizzas. We have X robots, X of them. Each robot can make Y pizzas. So this robot can make Y pizzas. Y pizzas. This robot can also make Y pizzas. This robot can also make Y pizzas. So in total, how many pizzas are produced? Number of robots times number of pizzas. X robots, each robot can make Y pizzas. Multiply. That was part A. Part B. Assume the cost of a factory is this. So here we're given some function. Okay, and they say for a fixed production of 1,000 pizzas. Fixed, that's a sign that I'm maybe being constrained, like I'm restricted in how many pizzas I can make. For a fixed production of 1,000 pizzas per hour, how should you allocate X, the number X, and productivity Y of your pizza bots to minimize cost? Minimize cost. So usually they ask you to like minimize or maximize the function. So my function is the cost one. It's the C, which is given as 3x squared plus 6y. My constraint is that I'm limited to only producing 1,000 pizzas. And how many pizzas like can be made per hour? That was part A. Like the total number of pizzas that can be produced is XY. And they're saying I can only make 1,000. So my constraint, I'll call it G, is that XY can only equal 1,000. Let me not call it G. Let me just say XY equals 1,000. That's my constraint. So because I have a constraint, I know I should use Lagrange. They also tell me to use Lagrange. Okay, so what does Lagrange say? It says that the gradient of my function equals lambda gradient of the constraint. I'll call this G. What is the gradient of C? Gradient of C is 6x, 6 equals lambda. What is the gradient of G? How do I write G? G is usually like a function. It's like something equals 0. So if I wanted to, I could rewrite G as xy minus 1,000 equals 0. If I wanted to. So what is the partial with respect to x? That's y. And the partial with respect to y is x. So what are the equations I have? The first row says 6x equals lambda y. Right, that's the first row. The second row says 6 equals lambda x. And also don't forget I have my constraint equation, which is xy equals 1,000. So if they ask you for like what does Lagrange tell you? You need to write all of them. Don't forget the constraint one. Okay, and now we solve. So multiple ways to solve it. You can solve it in any order, whatever you want, as long as it works. So let's just take the first equation and let me solve for lambda. I get 6x over y. Let me take the second one and also solve for lambda. Lambda equals 6 over x. And I'm going to set them equal to each other. Okay, so I get 6x over y equals 6 over x. So 6x squared equals 6y. Divide by 6, x squared equals y. All right, so now I get to this point, and now I'm like, wait, I'm stuck, right? But no, I'm not stuck. I never used the third equation yet. Let's use the third equation, which says xy equals 1,000. And I just found that y equals x squared. So why not just use that? X times, let me do in the correct colors. This is x. Y is now x squared equals 1,000. So x cubed equals 1,000, or x equals 10. If x equals 10, what is y? Well, now I can plug back into this constraint. X I now found is 10, so that means that y is 100. So final answer, xy of 10, 100 minimizes the cost of my pizza bots. Okay. Questions on volume 2. Okay. All right, let's go to volume 3. Also, I might have to extend. I think I put 2 to 5 p.m. I might not finish at 5 p.m. since we're only on volume 3. So I'll just keep going. Okay. Unless people want a break. Okay, we'll keep going. All right, volume 3. All the integral stuff. So we have double integrals, triple integrals, all those application stuff, and the different coordinate systems, right? Polar, cylindrical, spherical. All right, double integrals. Here I just wrote like Fubini's theorem, which is like how you do like why you can do double integrals the way we've been doing them. I'll just skip over that. Oh, recall that the formulas, area equals the integral of 1 dA. If you want to find the average value, it's always that integral where you have f in the integrand, and you divide by the integral with 1 in the integrand. Okay, so that's always the average. Same with triple integrals, right? Triple integrals, if you wanted to find the volume is in triple integral of 1 dV. And notice that average is, you see, you have the integral with f in the integrand divided by integral with 1 in the integrand. So remember the average formula? Okay, let's see. Okay, let's consider this integral. I won't actually do it, but I think the second part is interesting. So let's say that we're given this integral and you're asked to evaluate it. And I'll tell you that the answer you get is 1 if you actually evaluate this. My question is the answer positive, negative, or 0? And does that make sense? Does an answer of 1 to this integral make sense? Well, Y and Z. Okay, first thing we want to consider are the bounds well ordered. Bounds well ordered. Why does this matter? Because think about in single variable calculus, if we were doing an integral from 1 to -2 of x, like usually we want the lower number to be on the bottom. So we would say like, oh, a negative sign comes out. That way I could do -2 to 1. Right? So if the bounds are not well ordered, like they're opposite, a negative ends up coming out. So let's look at our answer. Our answer is positive. All of the bounds look well ordered. 0 is less than 1, -4 is less than 2. This y squared is less than square root y, because if I wanted to draw the yz bound, this is z equals y squared, and this is z equals square root y. So this is lower than the blue one, so good. Bounds are well ordered, so everything should make sense that it's positive. All right. Second thing to consider though is also the integrand. Can our integrand be like negative or positive? Let's look. We have 2yz. Y is always between 0 and 1, so y is always positive. What about z? Z is between y squared and square root y. And if y is always positive, these also have to be positive. So our integrand is always positive, no matter what. Like the region we're integrating over will make the integrand always positive. So well-ordered, integrand is positive. The answer is positive, makes sense. Questions? Okay, and here I just wrote the things to remember. If you have a area of a 2D region, that's a double integral of 1. For 3D stuff, you have that if you could do a double integral of f to get the volume of this 3D object under f. Like this is f here. I could get, yeah. And then triple integral of 1 is the volume of a 3D thing, and then so on. Okay, ln the average formulas. All right, applications in geometry. These are just a lot of formulas to know. So like the centroid, don't forget what the centroid is. Think center. So you can find the x centroid, y centroid. And how do you do that? You take the integral of x over the integral of 1 for the x centroid. For y, your integrand is y instead. So you could do that in 2D and 3D. Let's see. I think we can you can check out this example in my notes. As I said, I'll post the answers so you can double check yourself. And feel free to email me if you think there's a typo or anything. Yeah, okay. Mechanics, what is there? There's the center of mass. Remember, for all these like center of mass, moment of inertia, radius of gyration, there's always this like density, because now we're using dm, which is density of dA or density dV. So again, center of mass, if you wanted to find the x one, you have x in the integrand, y has y in the integrand. Moment of inertia, what is r? R is the distance from any point to the axis you're rotating about. What if the x partial integral was negative? X partial integral. Where was x partial? Where was this part? In the equation where, in the equation where the answer was 1. What if x partial integral was negative? If your integrand was able to have like negative values, then maybe it wouldn't make sense that you have a positive number, unless something ends up like canceling out maybe. Like maybe you might have a region that's like this, where your integrand has some positive, some negative, and then you get an answer of 0, then that would make sense. Like your symmetric region. If these bounds were switched, like this said -4 and 2, then an answer of positive 1 would not make sense because your bounds are not well ordered. Good. Okay. Let's see. Okay, mechanics. Right, radius of gyration. Center of mass. All right, features of center of mass versus centroid. Right, remember centroid, think of like the center. Where is the center of your shape? And center of mass is almost the same thing, but with a density. Okay, but there's a caveat. If the density turns out to be constant, meaning like when you're computing center of mass, dm is rho dA, right? Or rho dV. Say your density is constant, like it's 3. Then in that case, the center of mass is essentially the same as the centroid. And how do you find the centroid or the center of mass if density is constant? You want to kind of like look at where is the middle of your shape. So if I had given you this like paraboloid here, and I told you that two components of the center of mass or centroid are like the nice to find points. Like you don't have to calculate anything. And only one of them you actually have to calculate something. Why? Because think about this shape. Where is the middle of it? It's probably like somewhere here, right? Like we have a circle, so it's probably like in the center, and then it's somewhere on like the z-axis. So it turns out that the x bar and y bar, those are the nice to find points because I know my circle is symmetric. So I know that my center has to be like in the center. That has to be 0, 0. And then z bar is the hard one because it could be somewhere on this z-axis. I don't know where it is. So that one I actually have to calculate to be like this. This is the formula for center of mass, right? Z in the integrand over 1 in the integrand. Similarly, what if I had this like cylinder shape? Let me make it like this. What are the nice to find points? Notice that my circle lives in the xz plane. So that means that the center will probably be like somewhere here, right? So x bar equals 0, z bar equals 0. What about y? Y is the one we have to solve for because it's not like centered. So y I would have to solve for using the formulas. Okay. Let's look at this question. Consider a rectangular prism defined by that, and this body is assumed to have unit density. What is the moment of inertia rotated about the y-axis? Show your work and set up the integral carefully. Okay. So we're asked to find the moment of inertia. What is the moment of inertia? Moment of inertia is the integral of the inertial element. We're in 3D here because of the triangular prism. Oh, and I drew out the triangular prism. X has a length of L, Y has a length of 2L, Z has a length of 3L. All right. What is the inertial element? It's defined as R squared dm, where dm is rho dv. What is rho here? We're told we have unit density. So let me do unit density. So this is 1 dv. R squared 1 dv. Question in the chat. When finding center of mass for the last problem, why didn't we do a triple integral instead of a double integral? Yeah, it would be a triple integral, sorry. Oh yeah, I guess there would also be a DC. Thanks for catching that. Why is it not a triple integral to compute the y in coordinates? Where here? Y coordinate would also, yeah, be a triple integral like this. And here we don't have any rows in the integrands because density is constant. So rho dv will be 1 dv. This is the case where density is constant. If the density were not constant, then yes, you would need a row in all these parts. Okay. Okay, so back to this, we have r squared dv. What is r squared? Or what is r, I mean? R is the distance from any point, x, y, z, to the closest point on the axis it's rotating about. We're rotating about the y-axis. That's this axis. So what's the closest point to that axis? Well, I would probably want the same y value, right? And everything else is 0. So how do I find the distance between those 2 points? I use the distance formula. Z minus 0 squared, y minus y squared, x minus 0 squared. So I get square root of z squared plus x squared. That is r. So that means that r squared is without the square root. Z squared plus x squared dv. Good. All right, and then what are our bounds? Well, we're integrating over this cube, right? So a cube, I can do in any order I want. Z squared plus x squared. I'll just write like dx, dy, dx, dz, it doesn't matter. Y goes from, in the problem, they tell me 0 to 2L. 0 to 2L. X goes from 0 to L, and Z goes from 0 to 3L. Okay, and I will let you guys integrate this. You get 20L fifth. Okay. Part B says, I want to rewrite this answer in the form of CML squared, where M is the mass and L is still the L length. All right, what is the mass, first of all, though? The mass is, well, the integral of the mass element. What is the mass element? It's the density dV. But we have unit density, right? So density is just 1 dV. What is the integral of 1 dV? That's the same as the volume of our shape. So what's the volume of this cube? Length times width times height. So it's 6L cubed. So if I want to write the moment of inertia, which I just found from part A, I found it's 20L to the fifth. And I want to write it as C times this mass, 6L cubed, L squared. Then what does C have to be? Notice the L fifths cancel. So I have 20 equals 6C. So C has to equal 20 over 6, or 10/3. Okay. And also part C then. Part C says set up an integral to compute y bar. Recall that the formula for y bar is the triple integral of y rho dv over 1 rho dv. What is this bottom part? This should look familiar. That's the mass, which we just found to be 6L cubed over the triple integral of y dv. Okay. Questions? Okay, then we have probability stuff. So probability, you have the expectation formula, right? Expectation of x, you have x in the integrand, y, you have y in the integrand. Variance, standard deviation is square root of variance. You also have these marginal density stuff. So if you wanted to find the marginal density of x, you do the y integral only, like use the y bounds, whatever it is, dy. If you wanted to find the y marginal density, notice that you only do like the x integral. So do like the opposite of what you, like the letter. Okay, let's do this question. So this is spring 2017 final. Actually, let's skip, let me do part of it. So part A, you're asked to find what, or let me like outline it. It says we're given this probability density function on the unit ball, which has radius 1. Okay, and they say that this density is this. They say that it makes a probability density on the unit ball. And what is K? If something is a probability density function, or a PDF, that means that the integral of it should equal 1. That's what it means to be a probability density function. So I want the integral of this whole thing, this k x squared plus y squared. This thing, I want it to equal 1. So you can solve for this integral. You're integrating over the sphere. You get some number, k equals 1. And so you end up getting k equals 2/3 pi k. 2/3 pi. Or sorry, 3 over 2 pi. I'll say that you should use spherical coordinates as well. It will be easier because we have a sphere. Set up but do not solve an integral for the probability that a randomly chosen point in this domain has z greater than 0. What does z greater than 0 mean? It means that we're always above, we have a positive z value. That means that we're always on this hemisphere part. So when you do your bounds in spherical coordinates, what should those bounds be? If I do d rho, d phi, d theta. Well, rho goes from 0 to the radius, which we have a unit ball, so it goes to 1. Phi starts at 0, and it goes all the way down to pi over 2 angle. And in theta, we're not restricted, so 0 to 2 pi. Okay. And actually, the answer you end up getting is a half. And so part C says, like, why does this make sense? Or actually, you don't compute it. Pretend you don't compute it. But I can guess that it's a half. Why can I guess that it's a half? I can guess it's a half because we have our probability density, it's because like our region is just half of the sphere. So I could probably assume like if I pick a random point, like I have a half chance that it's going to be in the top and a half chance that it's going to be in the bottom. So I can guess that it's half. Okay, that was that question. Questions on that question? Okay, so let's see. We have polar coordinates. Thing to remember about polar coordinates is this r dr theta when you convert to polar coordinates. Cylindrical coordinates, you have these conversions. Remember in cylindrical is just the 3D version of polar coordinates. So cylindrical and polar, see how the x and y both have r cosine, r sine. Cylindrical just has this extra z equals z. Spherical coordinates, you have these conversions, right? And I'll say that like if you're given some Cartesian equation and you convert to spherical coordinates, some common things are that if you get v equals a number, that's a cone. Yeah, I think that's the common one. V equals something is a cone. Okay, let's see. We have the substitutions. Change of variables theorem. That was an important theorem. That's why all those like coordinate changes work. We can do an example. So let's see. Actually, let's do an actual like a final question. The question above is also interesting. You can look at it on my notes. All right, but this is from spring 2017. Compute this seemingly impossible integral by using change of coordinates. All right. So at first glance, we see this like complicated thing. And you're like, I don't want to take the partial with respect to y, right? So that's why we want to use change of coordinates. And they give it to us. They say that u equals x and v equals 2y minus x. What does the change of variables theorem say? It says that, well, right now I have dx dy. And I want to change it so that it's in du dv. Change of variables theorem says that it equals the partial of, remember whatever's over here, I put at the top. Whatever's on the bottom, or to the right, I put on the bottom, du dv. This is what the change of variables theorem says. You can almost imagine like the variables here are on the top, these are on the side. All right, and where this notation is the derivative matrix, where x and y are your outputs, so the things on the top are your outputs, and the things on the bottom are your inputs. Okay, but this requires having x and y as outputs. In order to calculate this, we need x equals like, I don't know, 2u plus v squared or something, and y equals u minus v cubed or something. That way we can find this derivative matrix. But we don't have x equals something, y equals something. All we have is u equals something, v equals something. So I need to use a relationship. I know that this derivative matrix, the determinant of it, let me be careful. This is absolute value of the determinant of the derivative matrix. Yeah. Okay. What if I take the reciprocal of it? Then these are equivalent. If I do the absolute value of the determinant of the derivative matrix where u and v are outputs and x and y are inputs, and I just take the inverse of it, that's equivalent to this. So if I want to switch the outputs and inputs, I can take the reciprocal. Hopefully you agree that's true. Okay. Given that that's true, now we can say dx dy equals that du dv. This is our theorem. All right, so now all we have to do is find what is this, the green thing. Let me put it in green. All right, so we have u equals x and v equals 2y minus x, right? So this is going to be the determinant of partial u x. The outputs are the rows and the inputs are the columns. All right, what is the partial of u with respect to x? That's 1. Partial of u with respect to y, there's no y, so 0. Here we have partial with respect to x is -1. Partial with respect to y is 2. Absolute value of the determinant, don't forget absolute value of 2 minus 0, which is absolute value of 2. Okay, so now I know that my integral, the like really hard integral, which I'll write out. This is what they wrote in the problem. E to 2y minus x squared dy dx. This equals, let me keep this here for now. And dy dx, we just saw it equals 1 over 2 du dv. Because the absolute value of this determinant equals 2. So dx dy equals 1 over 2 du dv. Okay, so I've changed the differential. That was one step. I also have to change the integrand. I need to make that only in terms of u's and v's. So let's see, what was my u and v? So I could write this as u to the 5th. This is actually the same as v, so this is exactly v. And here, this is also v, so this is v squared. So I've changed my integrand and the differential to all u's and v's only. What about my bounds? Okay, the bounds now, let's look at what our original bounds were. Our original bounds were that y is between x over 2 and x over 2 plus 1. Let me try to like manipulate this so that I get some complicated thing between two numbers. So meaning, let's try and multiply everything by 2. I get 2y like this. And then let me subtract x on both sides, every side. And notice that this is exactly what we said was v. That's what we made v. So we know that v goes between 0 to 2. What about x? X was originally 0 to 2. In the original problem, x was 0 to 2. And what was x? We made x u. So u is also just 0 to 2. Okay, and then we can solve that integration. Any questions on change of variables? All right, then we have scalar surface integrals. So this was all like the surface integral stuff, where if you're given a surface and you have some scalar function over that surface, then the surface integral is given by g d sigma, where d sigma is your surface area element. If you use different notation, that also works. This is the notation that I used. So let's just do an example. This says, set up an integral to compute the area of the surface. So the fact that it's a surface, we know that you can't just do like 1 dA, like an area of a 3D thing. You have to use the surface area element. So area of surface is like surface area. So you want to do the integral of the surface area element. Let me not write, yeah, surface area. All right, what are the components that we need? Or actually I can write. It's going to be 1 of the surface area element. What is d sigma? D sigma, the surface area element, is defined as the partials cross producted and taking the length of that, du dv. So this is my parameterization, my S. I need the partials, so let me compute the derivative matrix for it so that I could get the partials. So the derivative matrix is going to be the partial with respect to u is 0 to u to u. Partial with respect to v is 2v, negative 2v, 0. And so when I take the cross product of it, what happens? The cross product is ijk 0 to u to u 2v, negative 2v, 0. All right. So we get I0 minus negative 4uv minus j 0 minus 4uv plus k 0 minus 4uv again. So this is 4uv, positive 4u, oh, 4uv all the time except negative at the end. All right, so we have that this is, and we want the length of this cross product. What is the length? It's the square root of each component squared. So we have 4uv squared plus 4uv squared plus that negative 4uv squared du dv. If I simplify this, I get 4 square root 3uv du dv. Okay, so all I did was find the surface area element. So now I can continue the problem. Surface area is integral of the surface area element, which I just found is this thing. What are my bounds? They actually tell me the bounds. U is between 0 and 2, v is between 0 and 3. 0, 2, v is 0 to 3. Okay. Questions on volume 3. Can you explain the logic behind getting the surface area element again? Right, the surface area element is, you always need whatever your surface is, you have to parameterize it first, which they already gave to us, but you could parameterize other surfaces. So parameterize the surface, get the derivative so that you have each of the partials, take the cross product of those partials, and then take the length of it. And that's the surface area element. It's almost like we have this surface, right? And what is taking the derivative do? Like, what are these two columns? Remember from volume 2 or a while ago from this review session that like the columns are the vectors that are tangent to my surface. So I get some like tangent vectors. And when I do the cross product, the length of that, what is the length of a cross product doing? It's kind of like doing an area almost, right? So it's kind of like getting this area of the plane spanned by the two tangent vectors. But we don't want like this gives me like kind of like a flat plane. We don't want the flat plane. We want whatever the surface is. Maybe the surface is like a little curvy. And so that's why we do like an integral to account for that curviness aspect. So it kind of like takes into account this plane that is like curved. Okay. So yeah, again, the columns of the derivative matrix are the tangent vectors to our surface. Length of a cross product is kind of like doing the area of the parallelogram spanned by those two vectors. Any other questions on volume 3 before we go to volume 4? Where does the 3 come from? 3. Where? This square root 3? Oh, yeah, it requires a little bit of simplification. So let's see. This is all 16u squared v squared plus 16u squared v squared plus 16u squared v squared. So this is square root of 48u squared v squared. Or in other words, let me write it as like 16 times 3 u squared v squared. And square root of 16 is 4. So I take the 4 out, 3u squared v squared, and the u and the v squared also can come out. uv squared 3. Okay. All right, volume 4, last volume. All right, this is all the line integral stuff, work circulation, and differential elements, and Green's theorem and Stokes' theorem, divergence / Gauss theorem. Okay, line integrals of scalar functions. So let me see. All right, I think I will go over this summary part. So the difference, you've seen maybe different definitions, right? Sometimes we always, no matter what, we have a parameterization and we plug it into our field. But sometimes we multiply by the length of the derivative of the parameterization. Other times we dot product by the derivative of the parameterization. When do you use which? Well, if you have a scalar, if you're trying to find a scalar line integral, meaning your integrand is some scalar function, or like the differential element maybe says ds or dl, then you want to use the length version. If you have a vector field, which is written as like multiple ways, it could be written as like something dx, or it could be written as like ijk's, then you want to use the dot product version. I have a couple examples there. Now, the main problem of the volume 4 stuff is like all this work stuff, work and circulation. So what is work? Work is defined as basically the vector version of the line integral. Because you have some vector field, you plug in your parameterization to your vector field, and you dot product it by the derivative of your path. So work is kind of like doing the dot product of your vector field with your path. So it's saying, is your path going in the same direction as your vector field? If it is, that's positive work being done. If your path is going in the opposite direction of your vector field, that's negative work being done. Now, what is circulation? Circulation is just like a special case of work where instead of just like any field, any path we have, specifically our curve is a loop. So if we have a loop, then that's circulation. But otherwise, it's like the same idea. If your loop is going in like the same direction as your vector field, that's positive circulation. If it's going in the other way, that's negative circulation. And Green's theorem gives us a nice way to calculate circulation, which, yeah, if they ask for like for example, that one quiz, it was like, what is the work 2 form or work 1 form? You write the field exactly as given. So if the field is given like 3i plus 4xj, the work 1 form is 3, or it's that 3 and 4x. The flux you do opposite way. So negative x is the first component. So it's -3 i, and then plus 4xj. Okay. But yeah, what is flux doing? Flux is mdy minus ndx, and it's the net tendency of the vector field to cross your curve. So whereas the work was the dot product of the vector field with the path, let's say a tangent vector of the path, the flux is going to be the dot product of the vector field, but with the normal vector of the path. Normal vector. Why is this important? Let me go over this question. Which was also a quiz question. So like they ask you like, what is the sign of like the work or circulation or the flux? How do you do that? So the work or circulation, as I said, you want to think about the dot product of the vector field vector with the tangent vector of your curve. So like over here, for example, like this first path here, the tangent vector is like the one that's touching the path, right? And the vector field is the blue one. So if I took the dot product of this is like almost orthogonal. If it was orthogonal, what does that mean? If two vectors are orthogonal, the dot product is 0. So here, our work is close to 0. What about like over here, right? My tangent vector is going in this direction. The vector field is also going in this direction. So both my tangent vector and the vector field are going in the same direction. They're flowing together. So here, this is positive work. They're going in the same direction. All right, so as I said, same direction, positive work, different direction, negative work, orthogonal, 0 work. What about flux? So that's for work in circulation. For flux, you always want to look at the normal vector of your path. Okay, flux, there's a few different possibilities that I kind of wrote out. If your normal vector and your path are orthogonal, sorry, normal vector and vector field, I should say, vector field are orthogonal, then the flux is 0. So what do I mean? Let's look at, where's a nice example? Like over here, kind of. Right? This is our path. The normal vector, remember, is the one sticking out. Tangent was like touching the path. Normal vector is like sticking out. Here, this is sticking out. My vector field is kind of going in like this blue direction. This is orthogonal, so the flux here is close to 0. All right, so that's for orthogonal. Now, regardless of which way your vector field is going, if your path is going left to right, flux is always positive. If your path is going right to left, flux is always negative. So, for example, left to right. Let's see. Or actually I have, yeah, left to right. Like here, in this area, my path is going left to right. I don't care whether my vector field is going like pointing up or down, whatever. This flux is going to be positive because my path is going left to right. This first path in A, my path is going right to left, so the flux would be negative. Okay, what about if your path is in a loop? If we have a counterclockwise loop, our normal vector points outward. A way to remember this is that pretend you're walking on your loop, walking on loop. Wherever your right hand is pointing, that's the normal vector. So if I'm walking okay, so yeah. So counterclockwise, normal points outward. If clockwise, the normal points inward, right? So like here, this D path, this is going clockwise, right? So if I imagine I'm walking on this path here, my right hand is pointing into the curve. So that means the normal vectors are pointing inside. Okay, so if the normal vectors are pointing inside, what does that tell me, right? I'm trying to do the dot product of the normal vector with the vector field. So I have this normal vector here. Let me pick a better example. This normal vector here. And my field, my arrow is going the opposite way. So if I took a dot product of these two vectors, they're going in opposite directions. So the dot product would be negative. So flux is negative here. What about over here? My normal vector is pointing inward, but my vector field is going the opposite direction. So the dot product would be negative. So over D, we have a negative flux. Okay, so that's for the loop condition. What about if your path is like is vertical, like going up or down? If your path is pointing upwards, your normal vector points to the right. If your path is going down, your normal vector points to the left. So let's see over here, right? Like kind of like in this region, our path is going vertical and it's pointing upwards, it's going up. So that means that my normal vector points to the right-hand side. But my vector fields are going the opposite direction, mostly. So that means that I have kind of negative flux here because these vectors are pointing in the opposite direction. Okay, and yeah, so this is kind of like the overview of work circulation and the flux. And I wrote out some explanations for each of the paths in my in the notes I'll post after this. But for general questions on this so far? Okay. Let's see. We have the independence of path theorem. That's a nice theorem. So if you have a gradient one form, that means that instead of actually doing the whole difficult integral stuff, you can just find your function, plug in the endpoint minus plug in the beginning point. Okay, and the f function is called your potential function. Let's see if I have an example. Maybe not, but let's do this example. So this is from Spring 2017 final. They say that the work done by the gradient field, or compute the work done by the gradient field, that. Okay, so they say compute integral of capital F. And they tell us that F is a gradient field already. So if they had given you capital F, you would have to do a bunch of work and try to find the potential function. But they already tell you what the potential function is. They tell you already. They say it's x plus 2y plus z squared. Because capital F is the gradient of this. So that means that capital F dot dx, my potential function is this thing, lowercase f. So I'm going to do lowercase f at the end point minus lowercase f at the beginning point, start point. What is my end point? Notice that my path is this helical path given by cosine t sine t, where t goes from 0 to 2 pi. So my starting point is at t equals 0. When I plug in t equals 0, what do I get? I get 1, 0, 0. My ending point is when t equals 2 pi. When I plug in 2 pi, what do I get? I get 1, 0, 2 pi. So I want to plug in f at my end point minus f at my start point. Okay, so when I plug in, I have 1 plus 0 plus 4 pi squared minus 1 plus 0 plus 0. So the answer is 4 pi squared. Questions so far? How did you know to use that theorem? Right. So I know that I can use the independence of path theorem if my field is a gradient one form. And just other question is just to clarify, the only condition for independence of path is that f is a gradient field. Exactly. So my only condition is that this capital F, what I'm integrating over, if f is gradient one form, then we can use this theorem, gradient one form. What does being a gradient one form mean? It means that it's equivalent to saying that it's the gradient of something. And they tell me that capital F is the gradient of something. So they already revealed to me that it is a gradient of a potential function here. And we use this potential function in the independence of path theorem. This is gradient of potential function. Now, if they hadn't told me that capital F is the gradient of this, like if they didn't give it to me and they only gave me capital F is like, I don't know, 1x I, or sorry, 2xi plus 3x squared j plus 5xzk or whatever. If they only gave me that, in order to see whether or not it's a gradient one form, I have to use the component test. The component test is where you check like every pair of partials, meaning if I let my field components, I'm going to call them M and P, I need to make sure that the partial of n with respect to y equals partial n with respect to x. So first component, second variable, second component, first variable. So see how the numbers swapped? That's how I remember which to check. And then I need m with respect to z equals p with respect to x. So third component, or first component, third variable, third component, first variable. So 1, 3, 3, 1. And I also need n with respect to z equals p with respect to y. So I have to take all these partials and see if this is equal, see if this is equal, see if this is equal. If all three are equal, then yes, it's a gradient one form. If just one of them is not equal, like if over here I get 2x is and 3y, that's not equal. So it's not, it fails the component test and it's not a gradient one form. Why didn't we find the gradient of that function before plugging in the start and end? Like, why did we not find the partials and why did we leave the values of the function the same? So why didn't we find the gradient of that function? We don't need to find the gradient of the function because we want to use the potential function. So what is the, see, this is what the independence of path theorem says. As the integral of a gradient one form, which means if it's a gradient one form, it could be written as the gradient of some function. It equals the function at the endpoint minus function at the beginning point. Yep. So yeah. So this problem, they already gave everything nice to us. They already told us what the potential function is and we could use it. In other questions, if they gave us like this capital F as some like weird thing and say we used the component test and we said, and we saw, oh yeah, it works, it's a gradient one form, then we would have to do the work and try to find the potential function, which is a lot of more work, find potential. And the way you find the potential function is you would take like this first component. I know that the first component of the vector field equals the partial of my potential function with respect to x. If that's true, well, how do I find f? I can take the integral of 2x. When I take the integral of 2x with respect to x, what is that? 2x squared over 2 plus some like other expressions with respect to y and z. So I know that like my function has to have at least this part. It has to have x squared plus some other expression with y's and z's. It can have y's and z's because if you imagine like taking the partial with respect to x, there's no x here. So it goes to 0. So we're still left with just the 2x that we need. And then I would take this expression and I know that the partial of my potential with respect to y, that has to equal 3x squared y. I can integrate with respect to y and I get 3x squared y squared over 2 plus some function with x and z's. And I also do this one. I know that this is partial with respect to z is 5xz, and I take the integral. This question I just made up so it doesn't work out as nicely, but usually you'll have some like terms in common, and you'll like the common terms are like, yeah, you'll see the common terms and it will make sense. What is f? F will be like this term plus this term plus this term. Okay. I guess another reason why it also makes sense is that like why the independence of path theorem makes sense is like if capital F is a gradient of f, what's another way of writing the gradient? It's like each of the partials, right? Partial x plus partial with respect to y plus partial with respect to z. So that's why I'm saying that if it's a gradient one form, this is the partial with respect to x. And this is the partial with respect to y. And this is the partial with respect to z. Other questions? Okay. Next we have the del operator, which I called the triangle thingy del. We have three different things. The gradient, which we've already done. Curl, you should also know. Remember, a nice way of finding the curl is using the determinant of this matrix. Divergence is a new one. Divergence is you like take the gradient, but instead of making it a vector, you add up all the parts. Curl tells us that how much there's counterclockwise spin in the vector field. Divergence tells us how much expansion or contraction the field exhibits. We also have this like nice sequence of what happens. The gradient takes a scalar function to a vector field. Why? Because let's say I have a scalar function, 3x y plus 5yz or something like that. What does the gradient do? The gradient takes the partial with respect to x. Okay, let me make this an easier example for myself. Like that. The gradient becomes 3, 4, 5, right? Which is a vector. Then the curl takes that vector into another vector. Because when you do the curl, you get like something I plus something j plus something k. That's a vector. And then what does the divergence do? It takes each of those partials. So it takes the partial of that number with respect to x, and it adds all the other partials with respect to y and with respect to z, which gives you a scalar number, some number, scalar function. So this is the kind of like sequence that happens. And if you do any two things together, you get 0. So these are the main facts. Curl of gradient equals 0, and divergence of curl equals 0. On quizzes in practice, I've seen them give the field as f equals some operator like curl divergence in front of the actual endpoint. So if the field was given as f equals curl operator of 3x squared, do we assume that entire expression as the curl? Would we have to do some computation to find the potential function, or is that potential function that end form that we see? Curl of 3x squared. I think that this might be that this like potential function is usually used for like gradient one forms, and this is like a curl, which is a little bit different. So if they wanted you to find like the curl of 3x squared, that means that they want you to do like, and I assume this would have like a I maybe. Like then you would have to like actually find the curl. But yeah, send me an email with that question and I'll look more into it. Okay, let's go into Green's theorem. Green's theorem gives us a nice way of finding the counterclockwise circulation. So if you ever have some region that is like a closed simple plane curve, so like some enclosed region, like a circle or triangle or square, whatever, some like 2D region, it's probably a hint that you should use Green's theorem. Let's see. Let's see if we can do this example. So this is from Spring 2017 final. They say consider the following path integral integrated over a circle radius r centered at the origin, counterclockwise oriented. Notice that they say counterclockwise. If they said clockwise, you would do Green's theorem and then at the end take a negative sign. But right now we just want counterclockwise. All right, part A, compute the integral over the circle of radius r. Think first. Okay, so they say that we have a circle. So circle. Now I could maybe do this in like parameterize the circle, and like you know how you plug in the parameterization and you dot with the derivative, but why would I want to do that? That's so much work, right? Instead, I notice, oh, I have a closed like thing. Maybe Green's theorem might be applicable. So what does Green's theorem say? It says that I could do the partial of the second component. Let me call this m and I'll call this n. partial of the second component with respect to x minus partial of the first component with respect to y, dx dy. What happens when I do that? The partial of this with respect to x is 1. The partial of this with respect to y is x squared plus y squared, dx dy. Okay, so now I have a nice integral. I could keep things in Cartesian coordinates because I have a circle, but if I have a circle, how about if I convert to polar or cylindrical? If I convert it to polar coordinates, what happens? X squared plus y squared is r squared. And the dx dy becomes r dr d theta. And now I have a circle of radius r. So what are my bounds? R goes from 0 to the radius. Theta is my entire circle, so 0 to 2 pi. Oh, and you want to be careful about these parentheses as well, because this r like distributes. So if you calculate that, you'll end up getting something like this. So that was Green's theorem. And part B is interesting. It says, using your answer to part A above, what value of capital R maximizes this integral? And show me that you still remember basic single variable calculus. So they're asking, what value of capital R gives me the biggest that this could possibly be? So I'm like trying to maximize this. I'm trying to maximize the answer that I got in part A. When you're maximizing something, what comes to mind in single variable calculus? In single variable calculus, you're given like a function, like 3x squared or something, and you're asked to maximize that. How do you do that? You find the critical points. So I take the derivative and I set it equal to 0. I find the critical points, and then I do like a second derivative test to like classify and see what it is. So that's the same idea here. Because right now, if we're trying to maximize this, well, this is a function in one variable. Because there's only, our variable is capital R. So this is now a single variable calculus question. And I do what I do in single variable calculus. I take the derivative with respect to R. And what do I get? I get 2 pi times R minus R cubed equals 0. To get the critical points, right, I'm solving for 0. So R times 1 minus R squared equals 0. So R equals 0 and R equals plus minus 1. And they said that what value of R greater than 0? So I know that it can't be 0 and it can't be -1. So the answer is R equals +1, maximizes this integral. Question, how do you know to use Green's theorem in part A? So because they're telling me that I have this path integral, so I see that I have like this vector field, right? I know that it's like it's the vector version of the line integral thing because of this dx dy. So I see that it's like some field. I'm trying to integrate some field. The other thing I notice is that I have a 2D 2D thing, an object, and it's closed. It's a closed circle. So if something's in 2D, probably Green's theorem. If something's in 3D, I would probably use Stokes' theorem or Gauss's theorem. Okay. And I want to use Green's theorem because the other way I would have to do this is I would have to parameterize my circle, like xy equals something, right? And then take the derivative of that. So I would say like my circle is this thing. I would have to take the derivative of it. And when I do the integral, I would have to plug in what is x squared, whatever x is squared, times y, plus 1/3, whatever y is cubed. And then I have to multiply by the derivative of x prime, plus, then I plug in the parameterization for x, times dy, and do a bunch of integration, which is a lot of work. And it's possible, I mean, but Green's theorem makes it much nicer. How do we know that r equals 1 is a maximum and not a minimum? You could do like the second derivative test, or like from single variable calculus, or yeah, probably second derivative test. Or you could try plugging in 1 and make sure that it's like a positive number. Yeah. Okay. Other questions so far? Okay, then we have differential forms. So this is all like a 0 form is just the scalar function. A 1 form, you have like the dx, dy, dz. And a 2 form, remember the order matters for 2 form. The order is dy wedge dz, dz wedge dx, dx wedge dy. And this came up in the previous quizzes, one of the previous quiz as well. How do I remember what's the correct order, by the way? I kind of like draw this diagram where I have the x's together, the y's, and the z's. And what I do is the first component is f1, right? The first fx. So I'm at the outer circle, and then I go inwards to get dy dz. Like that's the first thing. Then how do I get the second number, the second thing? That's f2. And then I go into the inner circle, and I skip the one that is like associated to. So I start at dz, dx. And then what is this third one? That's fz. I go to the inner circle, and I get dx, dy. So that's how I make sure I remember like what's the correct order for these 2 form. And then a 3 form means that it has like the 3 wedges here. Then there's the thing of like the forms eating vectors. So a 1 form can eat 1 vector, 2 form can eat 2 vectors. How do you evaluate a 2 form eating 2 vectors? You can instead do the determinant of your vector field with your point plugged in, and then each of the vectors as columns. And then you have a 3 form eats in 3 vectors. How do you calculate that? Well, again, you take your field and you like plug in your point, but because we have 3 vectors already, we take the determinant of those 3 vectors. Okay, so let me do an example. This is from spring 2017 again, and it says the evaluation of the 2 form on the ordered pair of vectors. So like evaluate this 2 form on the ordered pair of vectors. So in other words, it's saying we have this 2 form and it eats in 2 vectors. How do you compute that is the question. Does eating the what does eating the vectors mean conceptually? Eating the vectors, it's kind of like it's like your input almost. Yeah, it's like your 2 form is like eating in the vectors. It's like taking in those vectors and trying to do something with it. Another way is also like, what does this wedge represent? Like dx wedge dy is the projected area to the xy plane. So by a 2 form, like 2 dx wedge dy, eating into vectors like u and v, it's like you have this u and v, and what happens when you project it to the xy plane? Like what is that area? What is the area of the u, v vectors projected down to the xy plane? Okay, so we have this 2 form thing. So we have let's see, there's 2 ways of doing this. The first way is using the formulas I had above, right? Where I have a 2 form eating in 2 vectors. I do the vector, or the field, I mean, ln vector vector. So what is my field? My field, remember, I have to write it in the correct order. The correct order, as you recall, is dy dz, dz dx, dx dy. So I have a dx dy here. So that's the 3rd component. And dz dx, that's the 2nd component. And I don't have a dy dz term. So that means my field is 0, -3, 2. So that's my 2 form written in the correct order. Then I have my vectors, and I write them as columns. And I take this determinant, and you'll get -19. That's one way. The other way is to do things more directly using only the forms language. So my 2 form is 2 dx wedge dy minus 3 dz wedge dx, right? So what did I say about this wedge product? Dx wedge dy is kind of like the projection onto the xy plane. So I just want to care about the x and y components of my vectors. This 1, 4, and the 0, -2. And then I have minus 3 dz dx. What are the z components? That's 2, 3. And my x components are 1, 4. And you'll still get -19. So either method works. Sometimes it's nice to keep things in the forms language, actually. Okay, questions so far? Okay, let's see, wedge products, properties. Remember that if we want to switch the order, a negative sign comes out. If you have 2 things wedged that are the same thing being wedged, you get 0. Also taking a derivative of the forms. So if you wanted to take a derivative of a 0 form, it's equivalent to the 1 form associated with the gradient of f. And if I wanted to take the derivative of a 1 form, it's associated to the curl. If I wanted to take the derivative of 2 form, it's associated to the divergence. Why is this useful to us? The reason is because, say I had a let's do the 0 form version. Let's say I have a 0 form field, right? Like 3xy plus 4y, like that. And 4yz. Let me just do 4z. Okay. And I wanted to take the derivative of this, df. How do I do that? Actually, okay, yeah. Yeah, how do I take the derivative? Well, it's equal to the partial with respect to x dx plus the partial with respect to y dy plus the partial of z dz, right? That's the derivative. Actually, let me not do that. Let me do a wedge example so it's more clear. Let's say I have a vector field, 3x, 4y, 5z. A vector field, the derivative of a 1 form field. So this can also be written as dx plus 4y dy plus 5z dz. Oh, none of these are gonna work out. Wait, x, z, y. Okay, let's suppose I have this 1 form. That looks like this, 3y dx plus 4z dy plus 5x dz. If I wanted to take the derivative of it, I have to do it component-wise, right? Like d of this is, I take the derivative of 3y with respect to the variable I have, which is y. So the derivative is 3 dy. And then I wedge on what's remaining, the dx. Then I have, this term has a z in it. So I take the partial with respect to z and I get 4 dz. And I wedge on what's left, the dy. And then finally, this term has an x in it, so I'm going to take the partial with respect to x and then wedge on the remaining stuff. So this one was a simpler example because I only have like 1 variable in each thing, and see how I just had to like do 3y, wedge on the other stuff. 4 dz, wedge on the other stuff. But if this was much more complicated expression, like there's a lot of stuff, like I would have to do a lot of different partials, right? And that would be like, that would take a long time. I mean, you could still do it, it'll give you the answer, but it'll take longer. And so the point of this tip is that instead of like taking the partial every single time, instead I know that the derivative of this 1 form is the 2 form associated with the curl. So instead I could take this field and take the curl of it. So f, my field, the field associated to this 1 form is 3y, 4z, 5x. And I can take the curl of it. The curl is ijk, partial, 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 3y, 4z, 5x. And I take, yeah, I find that curl. which it should give me, let's just do it. It gives me 0, 0, negative 4i minus j times 5 plus k times 3. So it gives me negative 4, negative 5, 3. And remember what is like the two form notation? The first term is always the yz one. The second is zx. And the third is xy. So look, do I have the same thing? 4 dz dy. Yes. Oh, I missed a negative sign here. Negative. So 4 dz dy is the same as negative 4 dy dz. This is the same as this. And this is the same as this. So see how we got the same answer. And it seems like right now this part seemed longer, but imagine you had way more complicated expressions in here. The curl would be much nicer to compute. Okay, questions on that? Okay, so this is the summary of like the derivatives. This is the forms length. Everything is like kind of the same, just in two languages. This is like the vector language. This is the forms language. All right, that's dictionary. Then we have surface integrals of vector fields. So in the two-form language, the surface integral or flux of f can be viewed as the surface integral of its associated two-form. So if you're trying to find integral of this flux two-form, then you can find the integral of f1 dy dz, f2, like you write it like this. Let me see if I have an example. I don't have an example, but there's I think there's a lot in like the Calc Blue book. So let me move on to Stokes' theorem. Stokes' theorem is the 3D version of Green's theorem. So Green's theorem is the same thing, just in 2D. Another way of writing Stokes' theorem in the forms lay is that the integral of this form is equal to the integral of the derivative of that form. Divergence theorem or Gauss's theorem is where you want to take the divergence in your integrand. Another way of doing it is like, another reason why is this true? The integral of this two form equals the integral of the derivative of the flux two form, which according to divergence theorem, it should be the divergence of f. Why is that true? It's all because of this. Over here. We saw that the derivative of a two form is the three form associated with the divergence. So if I take the derivative of a two form, it's the same as the divergence. So derivative of two form is divergence. So that's why we can do the divergence. Okay, and here I have an example from the spring 2017 final. So it says compute the flux of the vector field where f is that through a boundary of the unit ball oriented outwards. Okay. So first thing I notice is unit ball. Usually if you see something that's like a three-dimensional shape, like a three-dimensional solid shape, probably a clue to use divergence / Gauss's theorem. And in fact, see, in case you're panicking about the derivative of secant, you shouldn't be panicking about that. Because one way you could have approached this problem is, like I said, you have to like parameterize this sphere, plug in all the parameterizations, blah, 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 a bunch of stuff. Instead, we don't want to do that. Let's just use divergence theorem. So divergence theorem says that the integral of f is equal to the divergence of f. What is the divergence of f? Well, the partial with respect to x of this thing is 2. And there's no x term over here, so that's fine. Plus, I want to take the partial with respect to y of this term. Notice that there's no y's in here at all. So I get 0. Right? I don't even have to take the derivative of secant because there's no y's in here. What about over here? partial with respect to z, there's no z's. So this is also 0 dv. So this is triple integral of 2 dv. What is this? 2 integral of 1 dv. And this is super nice for us because the triple integral of 1 dv is what? The volume of our shape. And our shape right now is this unit ball. What is the volume of a unit ball? It's 4/3 pi r cubed. In this case, our radius is 1. So final answer is 8/3 pi. Questions on this problem? Okay. And finally, this is just like a little chart I made of the integral theorems. So like Stokes and divergence theorem, it's always like either, oh, I guess for Stokes theorem, sometimes you want to find the left side, like the parameterization version, but that's too hard. So instead, that's why we use the curl. Like you find the curl and then it's much nicer. Other times, maybe you want to find the, like, they're asking you for the curl version, but that's too hard. So instead you like use the boundary formula. Divergence, it's usually always this direction. Like this one is too hard, so instead you find the divergence. And in terms of like curves, you have the fundamental theorem. Remember the independence of path theorem. Okay, and yeah, 3 main integral theorems. And that's it. Okay, that's the end of the review session and for spring 2024, Math 1410. Okay, let me stop the recording.